3, 2, 1. We'll do a quick test run, just make sure that audio is coming through okay. All right, well, without further ado, we'll kick off. We're going to have a look at our AT7 assessment for the battery storage design and install component for on-grid PV storage systems, or PV systems with battery storage. And so in this Grid Connect Solar and Battery course hub, we find, just like we have with the rest of the content, we just go down that left-hand side of the page to find our actual course we're working on, the battery storage systems for GCPV systems course content. And of course, we've got our typical stuff there, study guide, PowerPoint presentation, etc. But now we are working on, this is GCwB, which is just short for Grid Connected Batteries, AT7. So assessment task number 7. This will only appear for you if you have previously uploaded a submission for AT6. And then you'll have this option here. So you can click on that. It'll take you to the next page with all the instructions here, just referring you towards choosing which file type you want to download. You've got the electronic copy on the left-hand side here if you want to fill it out on a computer. And then you've got a printable copy, just a PDF, which you can then print off if you prefer filling it out by hand. And then if you've got means to be able to scan it back in and upload it to Connect as your submission. Things to look out for when you're doing that is just how you print it may make it easier or more difficult for you when you come to scanning it. For example, if you've only got like a scanner that does single-sided, maybe it's worthwhile printing out a single-sided copy of the assessment. Obviously, it'll be a lot more pages, but then it just enables you to be able to scan it back in. Or otherwise, you might want to go to Officeworks or something like that to scan it in. For today's purpose, because I'll be filling it out on the screen, I will use the electronic copy on the left-hand side here. So I'm just going to open that one. It downloads down to the bottom left here as a Word document. I'll open that up. And here we are. So these assessment tasks, both AT6 and AT7, are both system designs. You will have noticed on AT6 it was called System Design 1, and this one now is System Design 2. And it relates to the unit UEE RE5001 because that is the design-specific unit out of this course. 4001 was the install-specific unit. Right. So that's our standard front page where you would normally, as a printed copy, pop your name and student number, signature and date on the front there. It's not as imperative when you're uploading it to Connect, however, because it's unique to your login profile. We've got all the standard instructions there for a written assessment. And then on this next page here, it just breaks down the overall task of the assessment for you. And you'll notice as we go through the assessment how this plays out. Firstly, with planning the design, we're basically looking at the site, simulating somewhat like we would in a real-world scenario where firstly you might have a discussion with the client, whether it's face-to-face or over the phone, and gather as much detail as you can that way to set yourself up, ready to go forward with the design, and then you might follow up with an on-site inspection, verify the details of things like the roof space, if you're using a roof, any specific site hazards and that sort of thing. Because remember, we've got to kind of think of in terms of being the designer only in this format. You may well be the installer as well, or you might not. It might be that you're preparing it for an installation team. So we've got to consider them in this process. After planning the design, then we can go on to doing the design as per step 2 here, design the system and everything that falls under that. And then third and final, documenting the design. So you will see in a couple of steps here, because we're doing a written assessment where we're trying to simulate a real-world scenario, it feels like a couple of questions are a bit of a double up because it's like we planned it first and then we did it and then we documented it sort of thing. So we'll just bear with the process as we go through. A reminder here that you've got the textbook, which has 3 scenarios which go all the way through the textbook. And on page 5 there, it's got the breakdown of each chapter in the textbook and which section it relates to. And remember, those three scenarios in here relate to the three different, what we call drivers or motivations, reasons why people get battery storage systems for on-grid. Whether it's for reliability in terms of they have a lot of blackouts or brownouts because they've got an unreliable grid access, or whether it's for offsetting peak loads. So they might be on a time of use tariff where certain times of day they pay a higher amount for their grid electricity usage and they want to try and attack that with battery storage, or maximising self-consumption being the third option of driver, which, you know, it might be, for example, they've always had solar and then now they want to add battery to it, and rather than exporting their excess solar to the grid, they want to store it in a battery for their own use at another stage, typically overnight. So that's what that's about. Okay, so here we land on the next page with our scenario, what we're trying to design for. This is our client. So this time they're in Cairns. So we're obviously a different location, much further north than Brisbane. And our location detail tells us a couple of things that's going to be pertinent to our design. What sort of things can you guys think of that our location dictates for us in terms of the overall design, solar and battery and everything? Yeah, 100%. Yeah. So our peak sun hours in terms of how much radiance, what are we actually going to be able to work with the solar and be able to produce how much energy per day. And of course, temperature is the other big one as well. In terms of, you know, location of batteries, whether we're going to need cooling, as well as all of our power equipment gear, inverters and stuff like that. And of course, within the irradiance too, considering tilt and orientation of our solar panels, stuff like that. Then we've got our energy usage detail. Just broadly speaking, it's 5 people in the house, you know, a medium to large household with relatively high energy use. What we've worked out from discussions with the client, and this may well be like your what we'd call desktop audit, you know, you've just given them a call and working this stuff out in the initial instance. Basically what they're after is to minimize their power bill by providing solar to all daytime loads and to minimize the demand charge. So they are looking at a time of use tariff. They want to run the entire house on battery storage during the peak demand period. So this period here, 3 p.m. to 9:30 p.m, is when they pay more for their electricity from the grid. Their DNSP, so their distribution network service provider being Ergon up there, has in this case, this is just a simulation case, but has offered generous incentives for customers switching to a time of use tariff, because they're always looking for ways to levelize the usage on the grid, you know, to avoid big peaks of consumption and that sort of thing. And one of the ways that they can achieve it is with a time of use tariff to incentivize people not to use so much during the peak periods by charging them more and charging them less outside of that. So they've got a secondary goal, like everybody does, to provide backup power during blackouts, because, you know, if you've got a battery there, of course you want to be able to use it when there's a blackout. Classic story, they're willing to pay enough, you know, to have good quality gear, but of course they want to get a return of investment of some sort. They would prefer the use of lithium batteries if this can be achieved. So the load profile is provided here. It's already been monitored. It says here, you have monitored the household load and found the typical load profile to be as follows. So maybe we've used, you know, solar analytics or some sort of energy monitoring that we've installed on the switchboard to get this data. And we've broken it up, we've spat out a report and broken it up into the different times of day to allow for that goal that they want to attempt, having a separate peak period, a 3 p.m. to 9:30 p.m. period. So what we can see there is during the normal daylight hours, which you can see, you know, 7 to 3, basically we're trying to attack daylight hours when the solar is kind of producing something significant. They consume 13 kilowatt hours per day. So it's important here, we always need to kind of pause at this point and remind ourselves of the basics, being the difference between power and energy. So energy is made up of power multiplied by time, and that's how we get kilowatt hours. That's why we measure energy in kilowatt hours. Whereas power on its own is just an instantaneous value. And that's where we measure it in like kilowatts or watts or kilovolt amps, as we can see here with the max demand, or volt amps, when we have an unknown power factor. So just important to remember the difference there when we are describing one or the other. It's a dead giveaway with energy. It's got hours in there, kilowatt hours. So that means there's a time quotient allowed for in there. So 13 kilowatt hours during the daytime, which is 7 till 3, 15 kilowatt hour usage during that peak period from 3 till 9:30, and 8 kilowatt hours overnight till 7 a.m. And all of those totaled together gives us a 24-hour usage of 36 kilowatt hours per day. Whereas on the max demand front, this is just, remember, an instantaneous peak at one period in time. So throughout that whole period of 7 a.m. till 3 p.m., the highest peak that they achieve or that they use is 6 kVA. And it will fluctuate anywhere under that throughout that period. Whereas during the peak period, because they tend to use a lot more appliances during 3 p.m. to 9:30 p.m, cooking dinner, running the aircon when they get home from work, all that sort of gear, they peak a bit higher at 8 kVA. And then overnight, their highest peak is 4 kVA. So because they're all instantaneous values, they're not accrual. It's not like they're running at that all the time. So that's why we don't have a total. That's why there's no total down here for max demand. And that, all of that detail we've just been through, as you can see here, is the summer load profile. And you'll see why when we get into having a look at this time of use tariff later on, that the high grid electricity cost for the peak period is only in summer. The rest of the year, they don't even worry about it. So the rest of the year we can see has a different load profile. So we've obviously done some very astute monitoring here and monitored the energy usage for a prolonged period of time, or maybe they had a type 4 interval data meter and we've been able to request this data somehow from their retailer. So you can see some slightly different figures there for the rest of the year. It makes sense what we would expect for a household in that part of the world, up in Cairns. You would expect that their energy consumption for summer would be a fair bit more than their winter because of cooling requirements. So here's a suggested strategy. Because after talking with the client, we worked out that, yeah, okay, they want to get the most bang for their buck. You've determined that they would be likely to consider a range of measures to achieve this, such as possibly switching to the time of use tariff. Obviously, it's been very well catered that way so far, with all of the energy breakdown and everything centering around that peak period of usage of 3 p.m. to 9:30 p.m. Look at, this is the thing, we want to try and approach it as holistically as possible. So encourage the client to enact energy efficiency measures. If it's an older house, there might be a lot of ways that we could help achieve this, as well as load shifting. So with our knowledge that we have so far with regards to solar and batteries, I think we could probably all agree pretty easily that solar is a lot cheaper for the amount of energy it produces versus batteries with the amount of energy you can consume through them. So it makes a lot of sense where possible to shift loads into the daytime, upscale the solar and possibly downscale the battery requirement. And then ultimately it's all going to culminate in the strategy of installing our solar and battery system after we've addressed all those other points. Okay, so we've got I want to try and open another one so I don't have to scroll back and forward. I'll just open another document here. Alright, so here we are at the back of the document, the last couple of pages on that assessment document. You've got your appendices. Here's our switchboard. It's not quite as friendly as the previous one from the AT6 design. It's going to be a little bit more work required here. And we've also got our picture, our rough site plan. Similar to AT6, the note here says some creative license is permitted with regards to the layout of the system equipment on this building, since multiple angles of clear pictures are not available. So all we're told is the location of the switchboard, which is pretty typical, where you'd expect it to be, just on the external wall of the garage, that's the western wall, because if we consider this compass location to be sort of laying on the same plane as the ground, we're looking at off to the back of the picture being north, and sort of the front of the house that we're viewing is kind of a southerly kind of direction. So the garage is pointing off to the west. So you can use, because you can't really see the roof clearly and all that sort of thing, you just make some assumptions about how you would lay out the solar panels to make them fit and where would be the most suitable location for the batteries and equipment. So that's what we're dealing with there. So first step is to plan the design, and some of these initial questions are pretty sort of should be fairly self-explanatory, fairly easy to understand, so we won't spend too much time on those. But here we want to assess the site, including hazards, switchboard condition, and potential equipment locations. Firstly, what we're doing here in this first table is examine the house plan and list the main potential hazards that the installer, will need to be aware of. For each hazard, list at least one suitable control measure. Answer in the white spaces in the table below, or as an alternative, you may submit your own workplace risk assessment document in place of the table below. So if you've got one, that you've used on a site recently that would mimic this particular site that we're working on here, then by all means you can upload that. Just make a reference in the assessment here that you've uploaded it as a separate file, but just make sure that it is for the same sort of site. Like I've had people before upload risk assessment for a site that is just PV only and there's no mention of the batteries, for example. So it might be easier just to fill out this table. What is the main hazards? Really, this doesn't have to be completely exhaustive. It's good for it to be realistic as much as possible. But one of the main things that we pick up on people needing to revisit and resubmit this risk assessment is just that they haven't addressed the main hazards that you'd expect on working on such a site. So let's just workshop those main ones now. What sort of hazards are we going to be dealing with this kind of work? Yep, fall from heights, of course. And what do we do about that, control measure-wise? Yep, could be, well, in terms of, so I guess you're talking about like edge protection when you say yep. And that may or may not be something that's viable for a residential site. I know everybody approaches that a bit differently. It can be more common on commercial sites, but edge protection is one way we could go. What else can we do? Yep. Fall arrest harness, that sort of thing. If you're following along with this, by the way, just wherever possible, put things in your own context using your own words and that rather than us all having identical versions. So that's cool. Fall from heights for sure. And I think a good one that you mentioned there too is like barricading the area with regards to falling objects from heights, I guess, is the thing, isn't it? Like when we're carrying things up the ladder and stuff like that, that might be where you want to barricade a drop zone, for example, so that it's not a risk to people who are on the ground walking around. What else have we got? Just focusing on the main hazards. There'll be a lot of peripheral ones that people can go with, but what are some main ones that we'd be very remiss to forget, other than fall from heights? Weather, yep. I would say that's another peripheral one, but yes, it's standard on every site really, isn't it, when you're working outside? Weather conditions, what sort of control measures do we need there? Yeah, yep. What do we call that? Like monitor, yep, weather radar. But then, of course, stuff like, wearing sunscreen, just sun protection in general, isn't it, really? Sun protection. Just thinking about also what we're actually working with, what sort of system, what sort of work we're doing, hazards that come about as a result.
Heavy equipment, like batteries are heavy.
Yeah, yep, for sure. Yep. Heavy equipment, yeah, personal injury, that sort of thing. So, yeah, just correct lifting procedures, whatever that may be, whether it's, multiple people doing a lift or whether you're using lift equipment. Could also be, PPE, like gloves, etc. To avoid getting your hands pinched and stuff when you're moving stuff. So some of the things that I'm kind of also getting at is like electrical shock hazards. And we know all about that, test, tag, lockout, that kind of stuff. The big one here too is that we are working with multiple sources of supply. So it applies to the solar, for example, because obviously once we've put enough panels in series, we're dealing with hazardous voltage. And same with the grid, of course. We're working on the switchboard. We've got to isolate the supply from the grid. And also, potentially the battery supply too. The other thing too is energy hazards, which are a bit more specific to the battery. And as per AS 5139, we've got to do a site-specific risk assessment based on the battery chemistry we're using. So there's an example risk assessment in AS 5139. And at this point too, I'll just remind us that we can access Australian standards via your TAFE login. Hopefully you guys have been able to do that. If not, go into Connect and just under the content, if you click on the content here on the Connect page and scroll down that left-hand menu, you'll find down towards the bottom this tab here, Library Info, Australian Standards, etc. And in there, you've got all the detail. You've got a link to the library page, a list of the applicable Australian standards for this course, just to give you an idea of which ones to download. You've got access to the Clean Energy Council guidelines as well. And then just a PDF document on how to access Australian standards online from our library. Make sure you do it while you've got a live student login enrollment, because then you won't have access anymore. And it is a bit of a muck around. Unfortunately, it's the way that Standards Australia keep hold of that intellectual property, obviously. So it's kind of a two-step process. Not only you've got to have your login to the TAFE library, which is off the back of your current student enrollment, then you've got to set up an account with TechStreet, which is like the distributor through whom we access the standards. And then you can log in there. You can access the standards online via their website. But if you want to be able to download it, you need Adobe Acrobat, as far as I understand it, to be able to open a PDF. And then you also need to download a plugin called File Open for Adobe Acrobat. And I presume that's their way of tracking how many people use it, access and all that sort of thing. Otherwise, if you don't have that File Open plugin, you won't be able to open the PDF. So this particular PDF document here just runs you through that anyway. So that's that. And there's a risk assessment in like a template risk assessment version example in AS 5139 for your battery chemistry hazards. So yeah, energy hazards is one we've got to deal with as well. And of course, we're just going to go about correct testing, handling, and installation, like maintenance procedures, which of course we're going to get from the manufacturer's documentation detail as to how to manage that battery. And so those, I would say, okay, working at heights, working with electricity and the energy hazards from the battery, I would call the major hazards. And then there's a lot of other peripheral ones, a couple of which we looked at, weather conditions, etc., that you could add in as well. Right, moving on from there, our next question, 1AI, part 2, is regarding the switchboard. So examine the photograph of the switchboard in the appendice at the back, which we've had a look at. Comment on available space for things like that and the switchboard's compliance status. construction type materials that it's made of. Answer in details if explained to a layperson. So what we're trying to draw out here is just you showing your understanding of what's required. So again, if we have a look at this image of the switchboard, could we, all right, so what we want to do is whack a solar and battery system on here. So we're going to have a couple of circuit breakers to add to the switchboard, obviously, with a couple of new circuits. Maybe we could just take the last bloke's lead and just add another couple of pole enclosure in there somewhere. Maybe we can screw it to the side of the box here. Okay, is there any problems with that? Or yeah? So what's the issue here? Yep. Yep, meters aren't mounted on a hinged panel. It's not the right material. We can see there in the bottom left that it's that chipboard stuff that's falling apart. Certainly not fire retardant rating. So we need the meters on a mounted hinged panel. We don't have enough space as well, obviously, at all. Not even for extra circuit breakers, let alone labelling. Any metering, you know, energy meters that we want to put in there, that sort of thing. So yes, we're going to be doing a full meter box and switchboard upgrade, aren't we, to meet those compliance requirements for the DNSP ergon, as well as 3000 requirements. So that's really what this answer box here is for, just putting in those details that we've just discussed. Okay, so moving on from that, our 1AI part 3 is about location of equipment. So we've had a look at the house plan. We want to list the potential locations for all of the below components and why. They're potential locations because at this stage we're still at planning the design, sort of our desktop study, so to speak, desktop audit. So if we have a look at our house again, if we start with, what's our first one? Is it the PV array? Yeah. What sort of locations are we likely to be using here?
North-facing roof, massive, flat, beautiful.
Yeah. And that's it. Yep, we can't really see it because actually we're looking at sort of the southeast, southwest faces of the roof. We can't see much of the north, northeast, northwest. So yeah, exactly right. We can use some creative license there. It's hopefully not too wildly dissimilar to the type of house that we're looking at. And that's right. Essentially, it's going to be anywhere there, northeast to northwest kind of roof orientations. Obviously, to achieve the greatest irradiance throughout the year, because we're still in the southern of the equator location, aren't we? So we still want to be kind of pointing into the northern sky. Albeit not too much of a greater tilt, because Cairns is not heaps south of the equator. Yeah. So that's cool. With regards to our power conditioning equipment, charge controller or grid connect inverter and multi-mode inverter, what sort of locations are we looking at there for this place? Yeah, underneath the house, like down here? Okay, yep, so switchboard being over here on the external of the garage. You're thinking there might be somewhere back there that can go underneath the house in the shade? Yeah?
I wrote in this one and the last one on like the battery room. Okay to imagine that it's like space available for a battery room.
You could argue that, yeah, maybe behind the garage there you're going to build some sort of a battery room. Yep.
Yeah.
Yep. Either of those are fine so far. Sometimes people opt to go in the garage. That could be fine too.
Yeah, this is lithium, so you can do that,
Yes, and that's exactly right, because the next question, sort of after our inverters, is going to be the battery location. And so, because we are steering towards a lithium battery, as per the client's request, and just because of the plethora of product available in the market these days, and to be able to suit their budget, that's most likely what we're going to come up with. There's considerations particularly to do with installation location, and especially underneath the house now becomes a big question if it's a habitable space. We've got to be considerate of where the battery goes because we can't actually install it underneath the habitable space or within the restricted locations of an entry or exit. So you can think about, for example, a veranda space like this around the outside of the house. You may be able to install underneath there. It just depends on if you've got windows or door accesses to a habitable space above it. We need to be outside of the locations either side. Try to remember 600 or 900 to the side, one or the other, depending on the battery type. So yeah, that's just one to keep in mind. The garage can be a fairly suitable location. The only thing we'd be looking out for there is things like temperature, because that is the western side of the house. So you can imagine in the afternoon it's going to get pretty hot in that garage. So you might want to incorporate some sort of cooling, extra ventilation for the garage. And if you installed it on that external wall of the garage, obviously on the internal part of that external wall, you are not backing onto a habitable space. Whereas if you installed on the internal wall of the garage, being where the garage meets the rest of the house, that's going to be a wall backing onto a habitable space. So then you'd have to incorporate your fireproof backing to outside of those exclusion zones as well. Whereas you could probably avoid that on the going on the internal side of the external wall there with your battery system. So there's a couple of options. With regards to your battery protection isolation, so whether you're using a switch fuse unit or multi-case circuit breaker, location for that is a little bit more flexible than with the lead acid system. That's where we've just got to be most careful that we're not, within the exclusion zone for venting gas of a lead acid system. Whereas here, it just needs to be within our arm's reach and readily accessible. So it's just going to be obviously in the same location as the battery. Our PV array isolation, of course, as we know, as per AS5033, we want it to be rooftop within the right distance of your array that you're isolating, unless you are somehow achieving the new requirements for AS5033 and not needing a rooftop isolator. And same with your down on the ground by your power conditioning equipment that's attached to the array. You may well be using an inverter that's got a compliant inbuilt isolator, or you could have external isolation next to it. And then your charge controller or grid connect inverter protection isolation. So we've already mentioned the DC one, and then with regards to the AC side of things, just depends on location with respect to your to your switchboard. So when we look at this here, probably in no case are you going to be within 3 meters and direct line of sight of the switchboard, because it looks like the switchboard's on the outside of that western wall, which would mean that your inverter, if you've got an inverter with for your AC isolation for your inverter, you're not likely to be within 3 meters in direct line of sight, because that would mean installing it on a western wall with direct sunlight on it, which is not recommended as per the Clean Energy Council guidelines for the inverter itself, but also would contravene the DC isolation location requirements if you're using that integrated DC isolator on the inverter. So you're likely to have it on the other side of the wall or elsewhere, like we've discussed, underneath the house somewhere. So we are going to need an AC isolator, which will just be, again, readily accessible within arm's reach of our inverter. So that's all of our locations that we're suggesting for each of those components of our system. The next question here is, and I realise that I'm sort of skimming past these, and obviously those who are accessing this video after today can sort of pause it and go through and fill out the answers. And for you guys today, if you've got any questions, just hit me up. I'm obviously not pausing to fill them all out because we're going through and discussing them, explaining them as we go. But we will go through the numbers. We'll focus more on that when we get to the actual design numbers. So this question here, we're just basically putting into our own words the client situation, their driver, so their reason, why are they going for a solar battery system, their budget, desired outcome, etc. The key thing is to summarise it in your own words. Sometimes people do copy and paste from above where we were given the client's detail, but the idea here is just put it in your own words. So really, it's the same old story that we hear often from clients, like, yeah, I want some sort of return on investment, but I want good gear. And of course, we want to make sure we address here their main key driver, which really is offsetting peak loads. They're going, I think we can get a sweet deal here if we go for a time of use tariff and try and minimise to basically zero our usage from the grid during that expensive time, 3 p.m. to 9:30 p.m. That next question, 1A, III, identify the relevant standards, codes, regulations, and manufacturer's requirements. So you kind of want to knock off each one of those as you list it here. For example, if we started with the standards, what key standards should we be referencing for an install like this? Yep, which are? Yep. 3000. Here's another scary one that probably haven't referenced for a while, but we all know very well when it comes to designing cables. 3008, yep. We know of it. Have we ever looked at it? Yeah. Rule of thumb comes into play a lot of times. Which does often work too, right? Like, I mean, if you... certain cable sizes and installations you've got a lot of experience with, you have once upon a time looked up, hopefully, in 3008. And when you've got an idea of something that should work, if you just jump up to the next cable size, it's, a lot of times you're safe. With regards to standards, all right, cool. Wiring rules, yep, absolutely. And a big one too that we need to be mindful of there is with regards to cable protection. That obviously we would remember from recent updates to standards. What are we doing with our DC cables? If we've got DC cables, if we're running a DC system as opposed to an AC system that would incorporate microinverters, so if we're running solar DC cables, or indeed battery DC cables, if they're going through wall sections and stuff like that where they can't move more than 50 mil away from the finished surface, such as a stud frame wall, where it's running down through top plates and noggins and that, then you need to have protection of WSX3 as a minimum, which essentially just ends up being steel conduit most of the time, or running external in conduit. And then we're often achieving that with our AC cables if we're running in that installation type with a 30 milliamp RCD. But you want to make sure that you can actually utilise that. Some inverters tell you the minimum milliamp rating is like 100 milliamps. So that doesn't really help when you're trying to achieve the requirements there. So you'd again have to be back to steel conduit or running it externally in conduit. What else? Getting a bit more specific now to this type of installation. What other standards? What standard governs PV arrays, installation of PV arrays? 5033, yep. What about inverters, connecting inverters to the grid? Nice, yep. 4777, and batteries. So 5139, that's kind of like our main one for this for installing secondary batteries, rechargeable batteries. So they're really our key standards. Yes, there's other offshoots we could go to and that sort of thing, but they're the main ones. So that covers us for standards. Codes, like I mean, it's in the question here. Anything come to mind? Can we recall anything? We stretch back to like apprenticeship days, the TAFE and stuff like that. Is there a code that ever got mentioned? Yeah, yep. So it's like the electrical safety code of practice, right? And regulation is related directly to that as well. So like if we looked up the electrical safety code, Queensland, 2020. So code of practice is 2020. Here's the practice and regulation, I think it's 2013. Yeah, electrical safety regulation. Yeah, so it all comes from the Act. Remember the flow, it goes the Act, 2002, regulation, 2013, and then the codes of practice come out of the regulation, 2020. So it might be a while since we've conferred with those things, but they all essentially have the same name, electrical safety code of practice and regulation. And that sort of kicks off all those key points in the question that it's looking for, standards, codes, regulations, and then of course manufacturers' requirements. We're going to be looking at manufacturers' installation documentation, essentially, isn't it? All of the products we're installing. So that really satisfies that question there. Okay, this is an interesting one. Next question, IB1. Identify the available components and configurations. Okay, so we're going to go through them from configuration 1 to 6 as supplied in the textbook, GCS, and also in the PowerPoint presentation that we've been through for this course. The one thing that I will mention about this is that this comes from the actual unit of competency. So you guys are studying in this course UEE RE 4001 and UEE RE 5001, which were written, keep meaning to, I can actually show you on training.gov.au. Anytime you want to get the details of a unit of competency that you're studying, you can look up here at training.gov.au under the National Register of Vet. And in the side here, you've got a spot where you can just search for a unit code. So UEE RE 4001. And it brings up all the detail on this web page, and you can download it in Word document or PDF, and it's got all the detail of what you're actually studying, what you're being assessed against, etc. And firstly, on the page, we've got the detail of where it's up to, when it was released. So you can see there, this unit was actually released in 2017. So it's, you know, already in terms of industry-specific stuff and product technology and that, it's already getting long in the tooth. So the reason I raise that is that when we're looking at this aspect here of configurations, they came up with these configurations based on what was known in 2017 as far as product capability and that sort of thing. So you'll notice some things have shifted a little bit, and we'll discuss that as we go through the configurations now. We just want to put into this table whether it's AC or DC coupled, and then whether or not we would consider it for this particular design for this customer, and then we want to put our reasoning in. Why are we considering it or not considering it? So firstly, let's have a look together at configuration 1, which is this guy here. There's a little giveaway in the PowerPoint. It is DC coupled. And just to reconvene on what the difference is between DC coupled and AC coupled, it all comes down to where is your energy coming from? Okay, it's coming from the solar in this case, and where is it being stored in the battery? So if you just drew a line between those two to find a connection point between where the energy is coming from, the solar and the battery, do you have to run through any AC connections, any AC cables? If the answer is yes, then you're AC coupled. If the answer is no, then you're DC coupled. So here, whilst we can't explicitly see it internal in the inverter, there is a potential that for whatever reason, it could run through an AC bus through the inverter first before getting from the PV array to the battery. Most commonly, there's not reason for that. So we assume in this case, the PV array comes in on the DC terminals, the battery storage connects on the DC terminals, and so it's DC coupled. Strictly speaking, this is a little bit of a typo as well in the textbook where this image comes from. It should really be called a grid connect multimode inverter as per, their strict terminology in the chapter where the inverters are discussed, which I think is it chapter 6? No. Chapter 9. Yeah, so chapter 9 in that GCS textbook in the first edition talks about the inverters, and on what page is it? Where the different types of inverters, I think it's pretty early on. Yeah, page 128, it talks about types of inverters. So it firstly discusses grid connect inverters, which for all of you guys who have been working with grid connect solar for a while are familiar with. Basically, what it's actually getting at, being called a grid connect inverter, is that it has an MPPT built in. So it's made for managing a solar array, even though the name explicitly means it connects to the grid and therefore operates only with the grid. So if you don't have a grid available, your grid connect inverter is not going to function. It won't. You can connect solar to it and then connect a power point to it, but you're not going to get anything out of it because it only responds to the sine wave reference from the grid. Moving on, the next one there, section 9.1.2 on page 128, is your multi-mode inverters, which, as it goes on to say, it means it's the type of inverter that can operate either with that sine wave reference from the grid or without it. So it can operate as a backup, like off-grid style inverter. And it goes on to say, normally this means that it's going to have a battery attached to it. And that's indeed how they typically function. Because obviously if it hasn't got a grid producing the power input for it, typically it'll be the battery doing that. And then finally there in section 9.1.3, it brings those two terms together. Grid connect multi-mode inverter, which is a bit of a nuance because obviously by now bringing in the grid connect terminology into a multi-mode inverter, it's not telling us that it can operate with the grid because we know that a multi-mode inverter can already do that. What they're trying to do is bring the unique factor of a grid connect inverter that it has an MPPT function built into it, maximum power point tracker, made for managing a PV array. So that's what it's saying, because a multi-mode inverter doesn't necessarily have an MPPT, and indeed often doesn't, most often doesn't actually have solar input. It's just an inverter that can operate with a battery on or off grid. So a grid connect multi-mode inverter means it can also operate in solar array. And that's what we're looking at on the screen there. This is a grid connect multi-mode inverter. So we've already determined it's DC coupled. Would we consider it for this site, this design, or wouldn't we? Yeah? Absolutely. It's a new installation, which means we don't have any retrofit considerations. So by all intents and purposes, it's really probably the most streamlined install, right? One product in the middle of everything to connect to. There's always pros and cons in that whole one product argument. People can go down the route of simplicity. But then when you go down the argument of, so less points of failure is what I mean by simplicity. Whereas other people can argue redundancy, which means that, well, yes, while you've got less points of failure, if that one point of failure fails, then nothing works. So that's one argument, but there's always pros and cons. It's simplicity for installation, which typically is going to mean more budget friendly for the client. One historical limitation to this kind of setup has been the power output capabilities of these inverters. So because you've only got one inverter there that everything's reliant on for the loads, you're limited to how much power it can put out, how much power it can convert. And up until recent times, for a single phase inverter, that's typically been about 5 kilowatts. But we are starting to see bigger ones than that on the market now, which is cool. So we're starting to have less of a limitation with that. Any other input on that one? Configuration 1. And obviously, like many of these as well, the other thing you've got is just product availability. What sort of products are out there that you can use? Do you like working with them? Do you not? Etc. The manufacturers that are behind them. That's always going to be a factor as well. So let's roll on and have a look at configuration 2, which now, as we can see there again, it is DC coupled because if you draw a line from the PV array to the battery storage, we only go through the solar controller, which is DC in, DC out. So it's DC coupled. Similar kind of functionality being DC coupled as the previous configuration 1, except now we've got 2 different devices. The priority of the PV array is, by path of least resistance to charging the battery. You don't really have the control with your inverter to be able to make a choice on that, prioritize the energy elseways. Would you consider or not consider any preferences, anything you can see about this?
I'd probably not consider because it wouldn't cover the loads efficiently.
Right.
Prioritizing battery storage.
Yeah. Yep. So that's a good point. Because it's prioritizing the battery storage, it's not prioritizing the loads. So it may or may not suit your customer's strategy. Yep. There's often an argument between DC coupled and AC coupled depending on efficiency in terms of, are your loads significantly daytime loads or nighttime loads? For daytime loads especially, exactly as you said there, it preferences AC coupled because you've got less conversion factors. Here, in order to get the PV array energy during the day through to the loads, we've got to go through a few more connections and components through the solar controller, through the multi-mode inverter before getting to the loads, as well as those cable connections to the battery, etc. Whereas we'll see with the AC coupled ones, it's a lot more direct. So it's good, AC coupled good for daytime. But if you had significantly more nighttime loads, there is an argument that this is more efficient for charging the battery during the day and therefore then being used at nighttime. The other, what seems to be like just an industry factor limitation to configuration 2 is that a lot of people are not familiar with using solar controllers, charge controllers, unless they've come more so from the off-grid background. So oftentimes they're kind of unfamiliar, don't like to use them. Another one is that you've got a lot more limitation with regards to product compatibility with batteries. So if we're looking at lithium batteries, one thing we know so far through this course content is that the BMS is absolutely essential. So to have a battery monitoring system that controls the charge and discharge of our battery, and therefore, because it's the boss, the BMS, it needs to be able to communicate with the inverters and any power conditioning equipment, including the solar controller. So in this scenario here, the BMS of our battery storage for a lithium battery, we want it to be able to tell the solar controller what to do, essentially, with regards to charging the battery. So you need that communication interface between them. And when you look around on products that are available in industry, you find a lot more inverters that have compatibility communication-wise with lithium batteries than you will find solar controllers. So that can be a bit of a limitation as well. One idea that I like to throw in there is also, though, is a bit of an unsung hero the solar controller can be in terms of oversizing your PV array, especially with grid connection limitations. So what we may or may not know, depending on our experiences when it comes to making an application to our DNSP, a network service provider, such as our Energex and Ergon's Essential Energy, is that largely it's based on the AC power rating of our inverter that's connecting to the grid, because that's what they're mostly concerned about. How much inflection will this inverter cause on the grid? You do still have to let them know what your PV array sizing and that sort of thing is, but here you can see how, because our PV array is connected to a solar controller rather than to a grid connected inverter, we're not so limited by the inverter's rating to the grid in terms of size in the PV array. So if for whatever reason you had need of a large PV array with respect to the ratio of your actual multi-mode inverter's capability, and you had a large roof space or whatever available, this could be a system to consider. Let's say it was a single phase site. What we do know is that blanket across our DNSPs in Queensland at least, you can only have a capability of 5 kilowatt export to the grid. You can have up to 10 kilowatt AC connection, but only 5 kilowatt export at one time. So that means that if you're going AC coupled, you can only utilize 10 kilowatt worth of inverters. And then if we're claiming SCCs, that's going to allow us to have 13 odd kilowatts of, it comes down to the manufacturer's limitations as well. If they're going to allow us to install more PV array, and the manufacturer says these inverters can handle this much PV array, all well and good. But you kind of decouple that a little bit more with a solar controller. You can sort of go bigger and bigger with your PV array. There may be applications where that could be suitable. So there's a few different ways you can go there, but yeah, we're just going to answer those questions there on configuration 2. We know that it's DC coupled, and really it's a matter of preference as to whether or not you would consider it for this design. That leads us on to configuration 3, and that's this one, the first of the AC coupled types with the switching device in between. And this kind of brings us back to what I was saying earlier about when they came up with these configurations was, you know, back in around 2017. Well, 2017 was when this unit was released, but there's a lot of preparation work that goes into writing it. So a lot of the content would have been written in probably a year or even possibly 2 prior anyway. So the need for a switching device these days, external of the multi-mode inverter, is rare, because that switching device, you know, basically changeover switch function, is in most inverters, multi-mode inverters, built in. Typically, the only reason I can think of you using an external switching device, you know, maybe if you want to get a bit clever with switching different loads and things like that, or you need to switch a larger load than what the internal switching device of the multi-mode inverter is rated to for current. So straight off the bat, my personal, you know, opinions on this is that it's a bit archaic, unnecessary to have that external switching device, because in most cases you would simply locate your multi-mode inverter right there where that switching device is, and its internal switching device would handle that functionality, which is what essentially we see happening with configuration 5. In some ways, configuration 5 is just locating the multi-mode inverter where that switching device is. Maybe, you know, if there was a strange retrofit where they had some old equipment on site, old inverters, you might use that, but yeah, I would think it would be rare. So that's configuration 3. Moving on to configuration 4. It's also AC coupled, as we see here, because when you follow the line from the PV array again through to the battery, you've got to see we've got to cross some AC cables in between the 2 inverters. So therefore it's AC coupled. Any input on that one so far, whether we would preference it or not, reasons why.
It'd be good at covering for the time period, probably. It would be battery storage fed to specified loads.
Yep.
But they'd probably be less efficient at charging the battery. Obviously, it has to go through two sets of inverters.
Mm-hmm. Yeah.
But still, that's what you do in retrofit.
Yeah, very suitable for a retrofit. If somebody already had a Grid Connect solar system there, it's quite easy. You know, you just come along another circuit to the switchboard. And don't get confused, by the way, by where they put these connection points for the AC. You know, you're not necessarily doing a separate connection outside of the main switchboard here. You would just run those two independently, an AC cable from the Grid Connect inverter to its own breaker, and the multi-mode inverter circuit to its own breaker in the main switchboard as well. One of the inherent limitations here as a result, yes, it could be nice and easy for a retrofit. Obviously, this site that we're designing for is not a retrofit anyway. But the other is that now you've got, in this scenario, two separate AC connections to the grid for those two inverters. So as per our AS4777 requirements, if there's a grid abnormality, you know, whether it's a blackout or a brownout or whatever, if the grid parameters go outside of voltage and frequency parameter limits, within 2 seconds your inverters need to isolate that AC output. So what that means in this case is that, okay, yes, on the DC and on the other AC, on the specified load output of the multi-mode inverter, it can still operate in a grid outage, but your Grid Connect inverter is not going to be any good to you, your solar. So in the instance where a blackout happened during the day, you're kind of shortchanging yourself on the capability of being able to still function with your solar power. Yes, you might have some battery storage there to use for your specified loads, but once it's used up, you're out. You could have been using your solar as well, but because of that requirement of this inverter to drop out its AC connection to the grid, then that's just an inherent limitation there. So it would work fine, but then you can improve on that particular point with configuration 5. And that's what we see happening here with configuration 5. Due to now relocating the AC connections so that the solar Grid Connect inverter doesn't go straight to the switchboard, but rather goes via the multi-mode inverter to the grid. Now you've only got one inverter grid connection point that has to drop out in a blackout. So therefore, your Grid Connect inverter for your solar can continue to operate based on the sine wave reference put out by your multi-mode inverter. So you can continue to operate all of your system, your solar and your battery and everything with the specified loads in a grid outage. So if you're going for an AC coupled solution, configuration 5 is definitely a good choice for a new install. And really, in my opinion, it comes down to basically configuration 1 or configuration 5, unless you are sympathetic to that configuration 2 set up with solar controllers for whatever reason.
Why would you opt for 5 over 1?
Yeah, good question. Why would you opt for 5 over 1 ever? And really, the main reason that I can see is just if you have that power limitation. So typically speaking, when you separate out those two functions into a Grid Connect inverter to manage the solar array and a multi-mode inverter to manage the battery and the load output, you can get bigger power classes of inverter. Whereas when you're putting them in together in one, I imagine there's physical limitations in terms of weight, heat, dissipation, creation, because you're putting all those functions into one enclosure.
They're never big enough to run a house, not even close. Barely a grid.
Yeah.
Like a hybrid solar battery inverter. That's to get like a really, really big one.
Yeah.
They're pretty well useless.
Have you had much to do with the Solar Edge energy hubs?
No, but I did have a look at it last time.
I think-
Tape thing. Yeah, you had like something to look at.
Yeah, I think they're up to, what is there? 9 kilowatts on a single phase inverter output with, I think that's with solar and battery. It has some limitations maybe when it's only running on battery alone. Right. Mm-hmm. Well, that's not helpful, is it? So it looks like, I don't know whether they're on the, oh yeah, Australia and New Zealand. So they go up to this SE10000H, which we'll have a look in the data down here. We can see its output AC on grid is up to 10 kilowatts, 10,000 VA. As we scroll down and have a look at the backup capability, so AC backup, if you actually lose the grid, yeah, 9,000 watts on that one there at 230 volts. So that's pretty decent for a single phase inverter hybrid. I think they're, as far as I know, they're sort of the largest ones on the market at the moment. Second to that, I can only think of like the Fronius Primo Gen 24s, which are only up to 6 kilowatts. Uh-huh. Yep. Yeah, and ones like, and some of them have a different rating for whether it's solar and battery together or if it's just battery alone. So, like the SunGrow is typical, where you get the 5 kilowatts out with the PV and the battery, but then drops back to 3 kilowatts, I think, or at least I don't know about the current model. I haven't done much with them if it's battery only. Okay, so we've done that. Oh yeah, configuration 5 we were up to. But yeah, obviously more cost. So there's all those factors to balance out for the customer, what they're after. Configuration 1 might be more cost effective for them. But if they want more power than what you can get out of the one inverter, then you might have to look at configuration 5. Because there's also the limitation of, okay, you could do configuration 1 and just parallel it, have more than one configuration 1, but there are things to look out for if they're looking for backup power, and I've had to do this just for the system that I just installed recently. I was using the Fronius Primo Gen 24, and you can only have one of those in backup mode. So they won't actually function in parallel in backup mode. So that's one to look out for. Whereas with some inverters that are multi-mode inverters, separate to the grid connect inverter function, such as like a Selectronic SP Pro, you could have multiple of them in parallel in backup mode if they lose the grid. And then finally we've got system configuration 6, which the nuance here is, again, the external functionalities that they're driving here, like a current transformer and transfer switch, are very commonly used now with inverters on the market, and in fact, built in. Like that transfer switch function is commonly built in to the multi-mode inverter, so you would be using that in configuration 5 anyway, along with a CT or energy meter you could put upstream in the main switchboard in configuration 5. But what they're trying to draw out here was the extra capabilities with those. The CT is there upstream of the main switchboard because, as you've noticed through all of these configurations, we have both non-specified loads and specified loads. The whole reason being, and it talks about this in the textbook, where is it? I think it's in the specified load section around chapter 5, I think. Chapter 5 is around selecting and sizing specified loads. I thought they mentioned it in there, but it may also be in the inverter chapter, chapter 9. Somewhere they talk about how typically these on-grid battery systems will not be sized to run the whole site off-grid because we've got the grid there. They're sort of saying, if you've got I guess the assumption is you've got a grid there, so most of the time it should be on. So you're really only using your backup off-grid function for essential circuits for short periods of time. It's not to say that you can't, it's just saying most commonly you don't. But you could well be sizing your system. It really just comes down to your customer's pocket, how deep their pocket is, how much they want to spend. You can by all means size the system big enough to run their house off-grid for as long as they want, sort of thing. So it may well be, even though all of these configurations have a non-specified loads shown there by the sort of house image, and then specified loads shown by the aircon picture. But it may well be that you could actually have no non-specified loads. And in fact, that is what will be the case with this particular client, because they want to be able to, you may have picked up in their scenario situation information given there, they want to be able to run the whole house from the battery storage during that peak period. Basically, they want to mitigate getting any of that higher cents per kilowatt hour rate during the 3 p.m. to 9:30 p.m. So effectively, that means whichever configuration we went for, it's probably a bit easier to look at configuration 5 here, you will not have any non-specified loads. We're relocating all of the loads to this specified loads location, and so they're going to run through the multi-mode inverter. That way, the multi-mode inverter's got the capability to use its internal switching, its internal transfer switch, to isolate the grid and just run the loads totally off of the solar and battery system. So that's all capable of being done as well with configuration 5 due to the internal relay in the multi-mode inverter. Whereas in configuration 6, they were trying to achieve that with this external transfer switch. To be able to isolate the grid via the transfer switch in the times when you want to run all the specified loads just off of the solar and battery system. So rather than the AC, outputs of the two inverters having to isolate, the transfer switch does that function and therefore enables both inverters to continue to function, similar to configuration 5. And by having this CT here upstream of the non-specified loads as well, it just enables the multi-mode inverter to feed power back towards the main switchboard at the right amount as per what the non-specified loads are using, and ramp itself up and down as a result without sending any excess to the grid, for example. Yes, it's basically a convoluted sort of approach to what you can do with configuration 5 anyway. So extra sort of unnecessary components these days. Is there any questions or input on those so far?
We were talking then about putting that CT in and being able to regulate it better for power assembly as well. With configuration 1,
yeah.
Do you not do that and put a CT on it anyway?
Yeah, exactly right. But I think because of the age of these configurations when they came up with them, I presume, just looking through the configurations, that the use of a CT that could communicate back to the inverter wasn't common. So they're kind of saying in configuration 6 now we're using these external components to achieve that. So I guess that means that in configuration 1, that inverter doesn't really know what's happening with the energy once it sends it to the main switchboard, whether it's going to the grid or the non-specified loads. But yes, you're exactly right, it's commonplace now. All right, cool. Hopefully we've got enough info there for that particular question we're looking at in the assessment. Question 1BI, and comparing the 6 different configurations on their individual merits. 1BI part 2. So now we just want to go through some some brands, so we can get some familiarity with what products are out there in the market. Look out for the yellow highlight sections, just directing us towards here. It wants us to use the products that are available in Connect as a starting point, and then add to this your own research. So that's just to help keep steering us towards using the products that are in Connect, just to keep it simple for everyone. So when we do go back to Connect, I'll just open another tab here. Under, again, you can always just jump back to the Content tab, and you'll see if you scroll down again this left-hand menu, once we're underneath the battery storage systems for GCwB systems course content, you've got this tab here, Product Data Resources. So that's what it's alluding to in the assessment there, that these are the ones for us to use. So you've got solar panels, a couple there, the Q cells and the Phono Hyperion to choose from. You've got only one charge controller to choose from, Victron. As far as inverters go, you've got a Fronius Primo, so a grid connect inverter, the Victron Multi Plus, which is a multi-mode inverter, the Selectronic SP Pro, which is a multi-mode inverter, the SunGrow SH5K-20, which is the grid connect multi-mode inverter, so a hybrid inverter. And then we've got lead acid battery. It's actually just the one Sonnenschein solar block. And we've got a lithium battery to choose from, a Sonnenschein one as well. So we're basically using all of those as a starting point. So we've got Q-Cell, we've got Phono, and then you can add whatever third brand of solar panel you like. If you're not familiar with solar panels yet, you can just Google it. Or if you've got a wholesaler you deal with, you can have a look at their information, their brochure or online website. Charge controller, we had the Victron there. And again, add to this your own research, find some other brands. For the grid connect inverter, we had the choice of Fronius and also SunGrow. Even though it was a hybrid inverter, it does that grid connect function. Multi-mode inverters, we had the Victron. We also had SunGrow and Selectronic to choose from. As far as the battery goes, we only have the Sonnenschein brand provided in Connect. You can have a look around, find some other brands or ones that you might know of, you can pop in there as well. So then we move on to question 1BII and identifying the available tariffs. So we're starting now to look at what has this customer got available to them in terms of energy retailer and what that's going to cost them so that we can kind of cost it into our solution for them. I know that this can be a bit of an area where some people don't like to delve into, and I completely understand that when it comes to the real world scenario with your clients. Not getting in the way. I mean, you can sort of point them and say, look, I've heard about these retailers. Maybe some people are kind of a bit risk averse in terms of professional indemnity. I don't know. But we're just doing it for the exercise here today. And indeed, I think this client being in Cairns, they don't have anything else to choose from apart from Ergon anyway. So we're going to compare the different tariff rates available to them. The assumption is that they're currently on tariff 11, the normal all-time use tariff that does not vary, because they're considering moving to a time of use tariff. So in Connect, we have provided in this same area where we were, the product data resources, there's also right at the top this GCwB resource book for assistance with 3 of these assessments, 83, 86 and 87, so hopefully you've already accessed that. For the other assessments, but in there is also these price fact sheets. You'll see on this front page the contents here. Ergon price fact sheets, including tariff 11 and tariff 12A. So we've just got to scroll down until we find them. It does tell us page numbers for them, but unfortunately this version of this PDF document, this resource book, doesn't have the watermarks. We did have a previous one that had watermarks for those page numbers, but you can use them by putting them into, so what was it, page 26 to 27. If you put those page numbers in here, because this is on Connect, has the page numbers there, page 26, and I just hit enter, that takes me straight to that first Ergon Energy price fact sheet. And as we can see at the top of the page, it tells us that it's tariff 11. I'll just zoom it in a little bit. Tariff 11 with tariff 31 and 33. All we're interested in at this stage is tariff 11. So if you scroll down, we'll see here the first one is tariff 11 residential. So it's all year round, as you can see, 1st July to 30th of June. Yes, this is an older one. This is from 2019, but that's fine for the purpose of this assessment. And we want to make sure we're looking at the price including GST, because that's what the assessment asks for. So we've got 27.8278 cents. They're very specific. Is our usage rate per kilowatt hour. And then we've got our daily supply charge is 97.8428 cents per day. Sure, I've got a red versions here. What else do we need to fill in there? Okay, then we also need our feed-in tariff. Where is it?
Would it be the 9.1?
Yes. Yep. Just going to whack these couple of values in. I'm lagging behind you guys just so that they look the same. And then, yes, when we go back to that document in Connect, our Ergon price fact sheet, we scroll down and you've got solar feed-in tariff options. So they have some different options here. The first one, as you mentioned, this is just a flat feed-in tariff, sort of all day, all year round, 9.369 cents per kilowatt hour. The 44-cent feed-in tariff, if you're not already familiar with, that's the solar bonus scheme, which is a grandfathered scheme. So that's not available to new customers. That's from years ago. And then we've got some varying options here. So as it says, solar time varying feed-in tariff from 3 p.m. to 7 p.m. for the peak period is 13.606 cents just for that period between 3 p.m. and 7 p.m. And then outside of that, it drops down to 7.358. So given, for this particular client, they're actually looking at using their own energy between 3 p.m. and 9:30 p.m. anyway, there's not really much incentive for them there. None, in fact. So we'll just go with that flat 9.369, which basically all that'll be is any spillover excess solar during the day that they export to the grid. So you'll notice in the way that I've put them in here, is in the format of dollars per kilowatt hour or dollars per day, hence where the decimals are. And obviously this particular assessment example is set up this way for the client, what they're doing with Ergon. Obviously you could superimpose it, you could do the same process here with any other retailer. just digging out the actual prices per kilowatt hour and supply charge per day, etc. So we're comparing there, firstly, the tariff 11 prices, including GST, is what we've put in, and then secondly, we also want to bring in the tariff 12A prices to be able to compare for our client's desired thing here. And you'll notice now we've got two breakdowns for a summer tariff and the rest of year tariff. Whereas for the tariff 11, we only had all year values, because we'll see when we look at the tariff 12A price sheet that it's got a difference between the different times of year. So going back to our resource book here in Connect, we need to find the next page actually. Scrolling down, we can see here the next page, energy price fact sheet, Mergon Energy, and it's tariff 12A. And as we scroll down the page to the same spot, you'll see here they've got tariff 12A, residential time of use summer, 1st December to 28th of February. And you've got the excluding GST and the including GST prices. So we've got 68.9326 cents per kilowatt hour including GST. That's just for summer during that period of 3 p.m. to 9:30 p.m. And then you'll notice, if you look down a little further, tariff 12A, res time of use non-summer, so the 1st of March to the 30th of November, the rest of the year, is 23.6214 cents per kilowatt hour, including GST, which matches, it's both in that 3 to 9:30 p.m. period and outside of that. So basically, the rest of the year effectively functions the same as tariff 11, just being a fixed rate, but a different rate, a different value to tariff 11. It's 23.6214, so it's only in summer, in 3 p.m. to 9:30 p.m. when it jumps up significantly to 68.9326 cents. And we've got a daily supply charge of 85.3908 cents. And I'll put those in a minute on that same one, but you'll see the solar feed-in tariff rates are the same as tariff 11. So that will look like, I'll just copy them across into here. Daytime is 23.6214 cents, or $0.236214 per kilowatt hour, and that's the same all year round apart from that peak period in summer. So daytime peak and night for the rest of the year is all the same. Daytime and night is the same for summer, and then it's just the peak period in summer, that is that exorbitant rate of 68 cents, which obviously our client is seeking to avoid anyway altogether. The daily supply charge is actually a little less than tariff 11 plan. But the solar feed-in tariff, as we saw, was the same. Alrighty, so next step, identify the solar resource data. So what would be an appropriate peak sun hour value to use for Cairns, and where did this value come from? I always like to use the Bureau of Meteorology. So if we go to just bom.gov.au, and then on the home page, you just scroll down till you get these buttons towards the bottom here. Climate and past weather is the one we're after. And then you get this left-hand menu down the left-hand side of the page. We're after weather station data. Click on that one. And it loads in the main section of the page. And you'll see here, by default, it's on rainfall, but if we drop that menu down, we'll change it to solar exposure is what we're after. And I find as well that you need to change its observations into monthly rather than daily so that you get the longer term data. And we're just going to whack in here Cairns. And then we just got to choose the correct Cairns latitude, Cairns, Queensland. And then you get a choice of Eurostations, and they're ordered from closest to furthest away. So it generally makes most sense, obviously, to use the closest one. But it depends on how much data you're after. So this graph loads below that, and it shows us, okay, so it's back to, I think that looks like about 1990. And, you know, if you were after significantly longer data, you could have a look through the Bureau stations, but I don't know that, yeah, any of them are actually much more than that are available for whatever reason. There'll probably be an old one in here somewhere, but anyway, I'm happy with that. That'll do. So then we just click Get Data and it'll open it in a new tab for us. And so what we're looking at is monthly, mean, daily, global solar exposure. So the average per day, per month throughout the year. And you will find by default it's in the units of megajoules per square meter. We just want to change it into kilowatt hours per square meter because that then relates directly to peak sun hours. So you get the data per month for any average day in each of those months throughout all those years from 1990. But what we want is if you go to the very bottom, you get this summary statistics for all years. And then we can just use the mean, so the average annual, we can see there is 5.4 peak sun hours. So because we're just using an average across the year, any day in the year, that's kind of the average peak sun hour data you're going to get. Of course, you can always get more detailed and go per month of the year sort of thing and break it down that way if you like. But for this purpose, so far, this will do the job. So 5.4 peak sun hours, and we could simply copy and paste that URL data from BOM to say that's where we got it from sort of thing. Or you could just type in bom.gov.au, that's fine. It is helpful to have the URL there because if it ends up being wildly dissimilar to this, like if people come up with 5 peak sun hours or 6 peak sun hours, then I'll be like, where did that come from? Because there may have been a mistake in sort of how they loaded the data on BOM or where they took it from. Right, so in assessing the client's energy usage, this next step here, we want to fill out for these different periods. We're pretty well just copying this down from previous data we looked at. So there's summer load profile, and we got that from our previous table right back up near the client information. Back up here. Essentially, it just becomes a copy-paste exercise because it was already given to us in all of this data here. So I will copy it straight in to show you. Okay, summer load profile was 13 kilowatt hours for the daytime portion, 15 for the peak, nighttime was 8. Red. And it totals as 36 kilowatt hours. (13, 15, 8 and 36). Rest of the year load profile, also we're just copying down from what we saw above, and I'm not 100% sure. I think again this is just simulating that whole plan the design, do the design. one day when I review these assessments, I'll work out what's been done there. So our rest of year load profile, we had there 9, 12, 9, resulting in 30 kilowatt hours. So we can, once again, we just see, like we did earlier, the disparity between the summer load profile and the rest of year load profile. The question about the client's loads, 1B IV Part 2, list the client's specified loads. You may recall doing this in AT6. It was actually listed down under the energy load profile. It was like fridge, lighting, computers, entertainment, this sort of stuff. What about this side here, this client specified loads? Yeah, exactly right. Yep, that's the right answer, is basically the whole house, because that was the information we got from their information that they gave us. Because during that peak period, they want to be able to run the whole house off of the battery system, so therefore the whole house will have to be specified loads. So next we want to select an appropriate energy strategy for the client. Firstly, looking at energy efficient measures. So 4 common ways that a typical household may be able to reduce their daily energy consumption. So, I think most electricians, probably the first thought that comes to mind is like lighting, right? Typical old school halogen or incandescent lights can be switched over to LED, much more efficient. What other sort of things?
Modern efficient appliances.
Yeah. Yep. Check out their appliances. Yeah, exactly. Some households have a number of fridges and freezers. You could, suggest for them they're going to save a fair bit if they upgrade those, particularly the older they are. Even pool pumps and things like that. I do remember, I'm pretty sure Energex did a incentive program some years back where if you could get a certain energy efficient pool pump, they'd give you a cash back, something like that. You could even think outside the box in terms of energy efficiency. Doesn't just mean the actual appliances that consume the energy, but also ways to reduce the loss of energy. So when we think about it in terms of thermal efficiency, like window tinting or glazing, curtains, blinds, stuff like that to keep the house cooler, insulation even, ceiling or wall insulation spaces. Skylights even, maybe, could be ways for them to have lighting in dark spots in the house without using electricity. All those sorts of things. The next step there is looking at load shifting measures as well. As I mentioned earlier, particularly with solar being a cheaper portion of the system, we can upscale the solar by shifting some loads that might normally operate at night time into the daytime. What sort of loads could we shift?
Machine, dryer.
Yep. Washing machines, dryers, dishwashers, yeah, for sure. Could run them on timers and things like that. Hot water's often a typical one too, isn't it? You could utilise excess solar to heat the hot water. This next part there, part 3, is just asking about, okay, how can the client, so we're looking at like habitual use, how can they, change their habits and that sort of thing to reduce their use during that peak summer 3 p.m. to 9:30 p.m. period. One thing that comes to mind for me is like cooling, particularly at those sorts of hours. They're going to be using aircon a lot, I would imagine, in Cairns. A lot of people, I think, come home, wow, it's hot in the house, let's turn that aircon on and crank it right down. As opposed to, well, let's think outside the box again. We might have solar producing excess energy during the day. Why don't we run it from whatever time earlier in the day, 9 a.m. or 10 a.m. or something like that, when we possibly have excess solar available a lot of the time. And before the house even gets hot, hopefully they've got decent insulation and all that sort of thing, and can keep that temperature lower without making the aircon work harder, and it's just operating whilst it's got that excess solar, and we possibly use less during that peak period. Then that's one thing that comes to mind for me anyway. Cooking could be another one. If they love, cooking with their oven and stuff like that, maybe you could whip out your cookbook and recommend some good old crockpot ideas. Slow cooker. Cook it during the day so it's ready before 3 p.m. anyway. Just keep it warm. Part 4 then, in terms of outlining an appropriate overall energy strategy, is really just about tying all of those strategies together. So we're going to implement all of the above and then design and size an appropriately sized, solar and battery system. So it's just about addressing their energy usage first, seeing what we can do about that in order to give them the most efficiently sized solar and battery system, rather than just running at it like a bull at a gate and just sizing their solar battery system based on whatever their original energy consumption was. We could be more efficient than that. So it goes on to tell us that they've got a new load profile, that they've taken your recommendations into account and enacted them, or some of them. And so we're going to be given the new load profile after the energy efficiency and load shifting measures have been put in place. Below, we've got a whole of year new load profile. So now they use the same amount whether it's summer or rest of the year. And you can see that in the table below. So what's our total daily energy consumption value now if we total those up? Yeah, yep, 27 kilowatt hours. So it's come down from what was previously 36 in summer and 30 for the rest of the year to now it's 27 all year round. So you can see how that's been worthwhile exercise to help bring down the potential size of the battery storage, particularly, maybe even the solar. And our max demand values have come down as well. I think we had up to 8 kVA previously during the summertime. So now our highest one is 7 kVA, so that's good. That's helpful with regards to our battery sizing and our inverter sizing as to the actual peak demand that they want to be able to service. Okay, so now we just want to lock in a configuration, a system configuration. Stage 2, design the system. Select suitable system configurations from the options examined in 1BI. Select one appropriate system configuration to investigate that could meet the client's needs and why you chose this. So what do we reckon? Number one, we could. One limiting factor though here, as you can see, it's going to want us to use products from the specification sheets provided in Connect.
Won't have on the output.
Yeah, because the only product that we've got for configuration 1 is the SunGrow.
You go to 5 and then you can use this electronic and that should be coming up.
Yeah. Yeah, because when we look at our product data resources here, out of all those inverters we've got to choose from, the only hybrid which would suit as a grid connect multi-mode inverter is the SunGrow SH5K. And when we look at the data sheet here, got max AC apparent power of 5000 VA, but then when you look at the backup data here, you can see maximum output power 5000, but then maximum output power battery is 3000. So if you happen to be running on the battery alone, you're down to 3 kilowatts. And we saw just there that we're wanting a max demand of up to 7 kVA. So yeah, you're exactly right. We'll have to look at something like the Selectronic. So yeah, we are looking at probably configuration 5. Exactly, I would agree with that suggestion. In order to get that, what have we got there? We will address this later on when we look at the different products in detail, but we can have a quick sneak peek at the Selectronic data sheets and just see what sort of power classes are available. And so here at the top of the data sheet, the AC outputs, you can see we've got all the different time periods, because your multi-mode inverters are like this, they can handle surges. So continuously, here you've got all day long, they can carry these amounts. And then you've got a 60-minute and a 30-minute period. So when we look at maximum demand, obviously it's not happening all day long. So whilst we've got a peak of this client expected of 7 kVA is the highest during a peak demand period of 3 p.m. to 9:30 p.m. That's not going to be for that whole period from 3 p.m. to 9. It's not running, for 6.5 hours at 7 kVA, because that would effectively be, 42 whatever kilowatt hours. So it's already over the maximum, the total daily amount they use. So we know it's not running at the max all the time. It really, in this case, comes down to a discussion with the client. But generally speaking, a max demand period is expected to be about somewhere between 30 to 60 minutes. So that's helpful when we come to consider our inverter data sheet. We're going to be looking at between that 30-minute mark and the 60-minute mark. So you start to look at these models through here, you can see somewhere between 7 to 5.3 kilowatts on that one, 11.25 for 30 minutes, and 8 kilowatts for 60 minutes. So it's looking like maybe that one might do the trick. And we'll come back to that for more detail as we go through. So for now, we just know we're aiming at configuration 5. Why do we choose that? Because of the products available to us and their power output capability. So now we're going to go in, now that we've chosen our system configuration, and designate the brand and model of each component, as we've been directed to use only the ones in Connect, and list the efficiencies of each. And there's a note there just saying you might need to change these later on. If you're doing it by hand, record it in pencil, but obviously we're doing it on the computer anyway. Because at this stage we don't exactly know what size we need of each one. We're just kind of having a go, and we'll come back to verify later. So out of the brand of solar panels, we've got either the phonos or the Q cells to use. I'd suggest we use the Q cells just because they're the larger power class of the two. They're both reasonably low now, comparably, for what's available on the market. The Q cells go up to a 295 watt, the phonos only go up to a 275. So I'll open that data sheet for the Q cell. It's the model name is Q Peak. That's the Q cells Q Peak, and we'll use the 295. Now, in terms of efficiency, really what this table is after is to help us later on when we come to working out the losses in our system as the energy travels through from one point to the other. With the panels, the thing is, when you read the word efficiency, you're going to go to the data sheet and find, like for example, on this one here, what efficiency does it give us? You can see here they quote an efficiency rate of up to 18%. And that sounds poor, it sounds terrible, and for most lay understanding of people about solar panels, they're like, why are they so inefficient? But what it means is that, as we know, the peak irradiance we can receive at ground level or sea level is 1 kilowatt per square meter. And just by nature of the products that we're using, this silicon technology and that sort of thing of converting sunlight into DC electricity, it's not 100% efficient, like nothing is. There's losses in everything. And in fact, as far as the technology gets us, particularly with this product, it can only convert 18% of the available sunlight. So that's what it's talking about. It doesn't come into play in terms of converting the energy through the system. That's our starting point. 18% of the overall sunlight is what gives us a 295 watt solar panel. So it's our starting point. We don't really need to take it into account. So it's neither here nor there at this point, whether you were to write down 18% for the efficiency or NA, for example, not applicable. Doesn't matter because we won't be using that value later on. The charge control is also NA because we're not doing a DC coupled system. We can choose our grid connect inverter. Which I think, as it turns out, we don't have a whole lot of choices anyway. Really all it was either the SunGrow or the Fronius. Because the Victron's a multi-mode inverter and the Selectronic's a multi-mode inverter. Any input thoughts on whether to choose the SunGrow or the Fronius?
Size on that.
Yeah, so the SunGrow is a 5 kilowatt. It's because it's the multi-mode inverter as well, the Grid Connect multi-mode. The Fronius is just the primo range, so anything up to the 8.2 kilowatt we could choose. But at this point, we don't know how big we need until we start designing it. There's another thing to be aware of too, which you may know if you've dealt with Selectronic before, and that is that they have a couple of options of grid connect inverters you can use which are classed as Selectronic certified. See this note up here? That's about Selectronic certified, using a grid connect inverter that's Selectronic certified, which is basically there's two options now, ABB or Fronius. And it means you pay a bit more than what you would for just it as a normal Fronius or ABB inverter, and it's programmed to operate on the communication protocol of the Selectronic inverter. So it can ramp it up and down as it needs to. It just tells the solar connect inverter what to do. And so what that results in, just as it tells us here, is that your continuous output can be up to 2 times the continuous output in that arrangement when you use those Selectronic certified inverters. But otherwise you're limited to just 1 times if you've got a non-Selectronic certified, just a generic AC coupled inverter.
They can communicate with each other.
Yeah. Via a comms connection.
Yeah.
So it's good because other multi-mode inverters, the way that they control grid connect inverters. For example, if you think about when is it important, right? Let's say that you've either got export limitation on the grid or the grid's out altogether. So you're not allowed to send any energy to the grid. The multi-mode inverter is going to be in charge of that. And let's say that the battery is fully charged and nobody's home. There's bugger all loads being used. So the multi-mode inverter wants to tell the grid connect inverter, I don't need any power from you. As we know, grid connect inverters just operate and they just want to push their power out. So what happens in that scenario it's going to raise its voltage, because that's the whole thing, right? We want to push current, so we're going to raise the voltage. The grid connect inverter wants to push the voltage higher than what it sees at the multi-mode inverter. So it's going to get to a point, because the multi-mode inverter is like, I'm not a load, I've got no load for you. And it's going to keep raising the voltage until it trips itself out, the grid connect inverter, on its own, grid parameters. And then, as we know, it's got to do the whole grid test timer for 60 seconds and then take another 6 minutes to ramp up to full load. So it's a bit clunky, at best. Whereas with a control from the multi-mode inverter, it can ramp it accordingly. So generically, when it's done generically, they do it on frequency shift. And so it pushes the grid connect inverter out of its parameters. I have heard reports, I've never come across it myself directly, but I've heard people complain of the frequency shift can be problematic for appliances, for other loads on site, and I can understand how that can happen. The benefit of it is that you can distribute the systems a lot easier. So say you had a roof on a building over there that's really suitable for the solar panels. So you put your grid connect inverter and solar panels on there, using the existing AC infrastructure, so AC cabling that's already there between it and another building on site. You can put your batteries and your multi-mode inverter in there. When you set your solar grid connect inverter into off-grid mode or frequency shift mode to operate with the multi-mode inverter, it can happen, just over the existing AC cable, which you obviously can't do, or a lot more difficult. You've got to run a comms cable if you want to do a communication protocol. But it's not a problem if they're co-located. If you've got both inverters in the same building, just a comms cable between them, and it's a lot more smooth of operation, usability of the solar grid connect inverter. So that's why what you end up here with, many people, particularly off-grid operators, favourite Spronius, as it's belovedly called, of a Fronius and SP Pro arrangement, and it works quite well. So yeah, we can go with the Fronius Primo. Efficiency-wise, it's a bit difficult because we don't know exactly which particular model size we're going to use, and they do have different. Different efficiencies. So we could take a conservative approach and just use basically the lowest efficiency. So you can see here the data sheet starts with like the 3 kilowatt models, 3.5, and so on up to 4.6. No efficiencies on this page yet. So you can see anywhere from, and we typically use, from a conservative design approach, the European efficiency rather than maximum efficiency. Zoom that in a little bit. So you can see they're ranging from 96.1 up to 97. Like, it never hurts to use a conservative value because these also are the maximum efficiencies. And inverters have efficiency curves as well. So depending on how heavily loaded they are, and particularly grid connect inverters like this, they are made to be most efficient at a higher load point. So usually around 60 to 80% or something like that. Whereas with multi-mode inverters, it's kind of the other way around. So it's all trying to target their most common operation point. Because typically speaking, most solar inverters, we are loading them up with the solar input up to around that 60 to 80% or even 100 or over. Whereas with multi-mode inverters, yes, they do these surges to allow for loads, but when you look at it on average over the whole time, they're mostly operating at base load. So it might be 20, 30% loading of their capability. So that's actually where their more efficient point is. So all this to say, kind of like, even using the lower values here, you could always go lower again. 90, 95, whatever, if you wanted to be more conservative, but hey. So they've got a 96.1 on the 3 kilowatt. I wonder about the larger ones. Let's see how efficient they are. And there's an efficiency curve for you, by the way. Okay, so that's on the 8.2. But you can see how, yeah, in this case, all right, so they're actually peaking not much over, well, depends on the voltage. See those different coloured lines? They're for different voltage operations, depending on what strings, how many panels you've got in series. the actual voltage operation. They can see when you're operating at 710 volts, that's obviously typically not much good for residential anyway. The blue is 270 volts, maybe that'll be more applicable. It is actually peaking, and they're not massive variations anyway. Like when you look at this scale of this efficiency, it's only a couple of percentage points, but it is peaking around that, okay, maybe just above 50%. Interesting. But again, yeah, you're only losing a couple of percent. So what have our larger ones got here? Once we get up into the 5 kilowatts and above. What's the efficiency? Oh, here we go. Okay, yeah, so they're actually more efficient than the smaller ones. So I reckon we just take 96%, because 96.1 was the lowest, and we'll just use a clean round number. So we'll give it a 96% efficiency. The multi-mode inverter, we're looking at the SB Pro. Let's have another look at its data sheet. Got my mate Robert from NHP trying to call me. So our efficiency here for our Selectronic SB Pros, all right, here they are down here. Looks like our lowest is in the 95% range. So there's a nice round number for us to use as well. We'll roll with that for now. %. And then for our battery, we only had the one lithium option in Connect to keep it simple for us. Which is this Sonnenschein. So this is the data sheet. Now this is the thing with batteries, and that's why you see here a couple of more than one document. We've got a number of documents for batteries, and that's because unlike what we're used to with our inverters and solar panels and that, where we get pretty well all the information we need on one document, one data sheet, it's not the case with batteries. Often you've got to go search on a few different documents. So that's why we've got a few supplied here under each battery type. So I've opened the data sheet here. And they just call it the Sonnenschein at Home Lithium 9, suggesting it's roughly a 9 kilowatt hour battery. So we can put that in for our model. And then we just need to find our efficiency. At home. Oops. And I think, if I recall correctly, the efficiency is not actually on the data sheet. I think it's in one of the other documents. So we see here we've got the cycle life recommended at the recommended depth of discharge, 80%. Some of the approved inverters, and that's getting at what I mentioned earlier as well with regards to compatibility with lithium batteries, because essentially they've got a little computer running them like a BMS. You need to have communication capability with it and the inverter. So you've got to confirm that compatibility with every product you want to choose before you go to install it. And then we've got all the battery technical specs here, or a lot of them, but not the efficiency. So I'll have to consult one of these other documents, which I'm pretty sure it's actually the operating manual of all things. Have a look here in the operating manual, and I like using, especially when you're opening it on Connect, or there's always word search options anyway in whatever file type you open it typically, but just type in efficiency in here. And it brings us to this technical key variables table on page 33. And so it quotes an energy efficiency at 25 degrees Celsius of 95 or greater than 95%. So that's a nice round number for us again. We'll roll with that. 95%. Okie doke. So we start moving into selecting the size of the battery storage. There's 4 design criteria, and we want to write those down in this following table and record the corresponding value that relates to that design criteria. So it's good to remember that with your AT6, the assessment directly previous to this one, it has a bit more guidance in it because it's meant to be a bit more of a guided version, whereas this one's meant to be for you to have a bit more of a go yourself. And it will have referenced a spot in the textbook that talks about this design criteria, which is in the chapter around battery sizing. And I think we're looking for, it's chapter 6, pages 90 something. Is that right? 90, oh yes, 91. So on page 91 of the GCS textbook edition 1, it's got design criteria for sizing the battery bank. And that's what we're answering this question here for. Criteria 1, as it's got in the book there, is size of the specified loads that must be powered during a disconnection from the grid. Powered off grid. It's an interesting one actually. Like, I mean, I've summarized it there as being powered off grid, but when you read through the textbook and it talks about a disconnection from the grid or a grid disconnection, it's not always explicitly talking about there being no grid available. It just means even times when you want to, a little bit like our client we've got here, they've got certain times they want to run their loads directly off the battery. It doesn't mean that there's been a blackout. It means they've actually programmed it to do that at that time. So a grid disconnection doesn't necessarily mean that it was outside of your control. It could have been that we did it on purpose. And indeed, there are some, in other situations, like when the client's driver is maximizing self-consumption, it may also be that, in effect, the system is running in parallel with the grid, but you're just trying to achieve the majority of it from the solar and battery system. Whereas your grid can still top it up, so you can continue to run those loads even if the solar and battery system doesn't have quite enough for it.
What size of specified loads on the AT6 I just wrote like 55% of its total use, because that's what it would look night time.
Yep.
Would that be right?
Yep, and that's one.
In this case, it would be the full load.
Yep.
All day.
Yep.
Window, the full load.
Yeah. So the size of specified loads that want to be powered during a grid disconnection. So in this case, this is the peak period.
Yeah.
And there's 2 parts to it, like power and energy. So we would record here, like when we go back to that table here, 7 kVA and 9 kilowatt hours.
Yeah.
So we're just saying in our battery design, we want a battery that can achieve that peak of 7 kVA, but also is large enough to deliver 9 kilowatt hours for the period. So 2 parts to it. Right, and criteria 2 is the length of disconnections from the grid / length of backup time required. So I'm just going to summarize that as length of grid disconnection. And again, we've already been given that just for that peak period, which is 6.5 hours, right? 3 p.m. to 9:30 p.m. Criteria 3, as per page 91 in the textbook there, is the frequency of disconnections from the grid. So how often? How often is it disconnecting from the grid? Yeah, daily, exactly. And it's interesting, isn't it? Because it sounds to us like their target really is the summertime, because that's the only time when they get this higher grid cost. So they do have some sort of flexibility. I mean, if the client really wanted to, for the rest of the year, they could do other things, they could program the system to only do it during those summer months, and then run it differently, like a maximized self-consumption system for the rest of the year, or just have it as a backup in case there's a blackout or something like that. It'd be hard to imagine why they would want to. You'd think they just want to continue reaping the benefit of their return on investment. But you never know. There's all sorts of other ways to increase your return on investment, if it's like a blockchain arrangement or something like that. If they get involved with someone like what Reposit Power used to do, or different programs where they can share their energy and sell it maybe onto the wholesale electricity market, and therefore increase their return on investment potentially. Criteria 4 then, as we see on page 91, is the time in which the system owner requires the battery to be recharged. This is an interesting one. What do you guys reckon? How long has that customer got for the battery to be recharged in their strategy?
That morning period.
Yeah, that's it, exactly. Yeah, you could argue, something like that, 8 hours from 7 till 3. The interesting aspect is that, okay, so I assume we've all had a look at a solar inverter when it's starting up in the morning at 50, 70 watts, whatever, as it slowly ramps up as more sun comes up into the sky. So obviously, where they are using it for their daytime loads as well as charging the battery, it's got to overcome the daytime loads effectively with configuration 5. The loads are basically the path of least resistance, essentially, before the multi-mode inverter uses that excess solar to charge the battery. So whatever their baseline of loads is, and if it's a typical household where people having brekkie, getting ready in the morning before they go to work, etc., probably the loads are exceeding the solar output, again, depending on the scale of your solar, the tilt and orientation, etc., and the available irradiance, until maybe they leave the house. So whatever time that be, could be 8 o'clock or something like that, arguably. So yeah, it's just interesting how these factors come into play. All right, let's have a look at battery bank voltage. What sort of battery bank voltage do we want? How are we going to determine that? There is a guideline there in page 91, the same page we're on in the textbook, at the bottom of the page, just with regards to, they've tried to give a simplified recommendation dependent on the overall amount of energy you use.
Would that still be for like lithium?
It's a bit different, yeah, exactly. And especially because they've only got 12, 24 and 48 volt ranges there. We're dealing with much higher voltage ranges these days in the 400 volt sort of range with a lot of our options. But what else might determine that or help us? Is there anything else in our system that we need to consider? Yeah, exactly, yeah. So what we're connecting our battery to, the inverter, we've got to know what it operates on. And so when we have a look in there at our inverter specs, electronic, we've got all these different models here, and it's actually in the model name. You've got 24 volt converters, 48 volt and 120 volt. And as you look down the page, we'll find the range. So DC inputs here. So for the 24 volt ones, they operate on between 20 to 34. 48, you can see there, operate between 40 to 68. And then the 120 volt, 100 to 170. So, which makes sense, right? I mean, we call them 48 volt battery banks or whatever, or a 48 volt inverter, etc. But of course, like everything, the voltage varies. It dips, and when the battery gets low, the voltage goes down. When the battery's charged up, the voltage goes higher. So of course the inverter needs to be able to operate on a range, and that also helps us with different battery chemistries, because when we talk in all these round numbers divisible by 2, we are talking about the classic lead acid battery, which is a nominal voltage of 2 volts. Nominal means midpoint, roughly, by the way. So that's about halfway charged, basically. Whereas when we're talking about lithium types, it could be anywhere between sort of 3, somewhere between 3 and 4 volts nominal voltage. So it's a very different, instead of talking about a 48 volt battery, we might be talking about a 54 volt battery for lithium. But fortunately, we've got this voltage range the inverter operates on to allow for both. So exactly right, we've got to consider our inverter as well when it comes to our battery operation. Plus, one more thing, in this case here, we've only been given one battery to choose from. What voltage does it operate on? I think the data sheet should tell us. So there it is at the top there. Nominal voltage 54 volts. So that's also going to help us when it comes to choosing our inverter. And we can look at it, even though this is going to be a double up, because we're going to do that later. But if we look at our two, there's only two 48 volt inverters, 481 and the 482. Earlier on, we were looking at their power output capability. We need 7 kilowatts basically, and we can see here, as we discussed earlier, max demand is typically somewhere between 30 and 60 minutes. So even at 60 minutes, we've got output capability of 8 kilowatts. So that inverter looks like it would be suitable for our power output as a 48 volt inverter to interact with that lithium 54 volt. So far it's looking like it could come together. So 54 volts, why is it suitable? Something along the lines of it meets power output requirements of the load and compatibility with the desired ultimate inverter. Something along those lines would be good justification, I think. So the next thing we're looking at here, 2CI, design the type and capacity of the battery. Okay, so this is where we're moving into working out what scale of battery, specific models we need. So firstly, we're going to look at the total energy. So I like to talk about it in terms of we scale the battery this way as well as this way, so to speak. Energy for the overall period of time, how much energy they want, but then also to be able to allow for those surges, those peaks of power output it needs. So there's a formula given to us, which is out of that similar area in the textbook where we've been looking. It's on page 92 actually in GCS edition 1. So what that formula is wanting to find out, and that there should be basically in brackets, is the total energy required during the grid disconnection. That's what that ETOT-GD stands for. And we can work that out by finding out what the EAC, so it says EAC peak, which just means the energy, AC energy, required by the loads during the peak period. And then divided by all the losses in the system. That's all it is. We're taking that value straight off of, if we look up here, I think it was that 9 kilowatt hour value, I think it was. Go back up to our load detail. See, during the peak period, it's 9 kilowatt hours. That's our EAC peak. So the AC energy during the peak period. And then what we've got to do is offset it for all of the losses in the system in transmitting it from where it's coming from to where it's got to go. And that is shown in the brackets in that formula. So the efficiency of the inverter times the efficiency of the cables times the temperature correction factor is what that last one is, temp. So if we look at, I'll pull up again our configuration 5. So when we're looking at the system, and I might even just do, I can do a snip here because then I can draw on it. Take that guy there. And what we're looking at, so this, obviously the PV array, this is where we're generating our energy from. But then, what it's got to do is travel through this DC cable. Okay, so we've got voltage drop there, cable losses. And then it's got to be converted from DC into AC through the grid connect inverter. So that's where our efficiency of our inverter comes into play. That's another loss. Then it's got to travel through these AC cables, either if it's going directly to the specified loads, or it could be being utilized to go to the multi-mode inverter. And then again, we've got another conversion efficiency of the multi-mode inverter from AC now back to DC in order to charge the battery. And then we've got to travel through this DC cable, so we've got more voltage drop there. So you can see there's a lot going on from the production of the energy in the PV array through to being stored in the battery. And then it could be, what if we wanted to use battery energy to export to the loads, export to the grid, and we're coming back through that same DC cable. Again, we're converting back from DC to AC through the multi-mode inverter. Got losses through that AC cable back to the main switchboard. So there's a lot of losses that can be accounted for in the system. So that's what we're starting with here. In order to correctly size our battery storage, we need to know how much the loads require, which is already given to us, that's that 9 kilowatt hours. But then, how much loss is there between the loads and the battery? So what we're going to do is go through this process of working backwards, essentially. We start with the loads, and I'm gonna get rid of all that so I can. Is there a way to get rid of all of it? All right, I'll just use the red. So to go from the loads here, that's like our end point, right? That's our goal, to get energy to the loads, the specified loads. So we're going to work backwards now. We're going to go, that's 9 kilowatt hours. Put a 9 there. And we've got a cable loss here through to the multi-mode inverter. We've got our multi-mode inverter conversion efficiency, denoted here by the recycling sort of sign, the circular. And then our DC cable loss, again, into the battery.
So the battery loss?
The battery loss we will account for on charging, not on discharging. So here we're considering discharging. So it's just those three things, and that's why we see them in this formula. Here, inverter efficiency and cable efficiencies. So firstly, we need to fill in here, okay, EAC equals the peak energy consumption only. Let's put our inverter efficiency in. We've got that box there with answer written in it. What was our inverter efficiency? And it helps to know which inverter we're talking about, right? Because we're configuration 5, we've got 2 inverters. So when we're tracing backwards, like we were just then, from the loads towards the battery, we're going through the multi-mode inverter. So that's the one we want. Which we can see here, we've given our multi-mode inverter efficiency of 95%. So when we're using, to put it into a formula, we want to do it as a decimal. So we'll go 0.95 instead of 95%. That's our inverter efficiency. And it goes on to say, okay, for your cables, we just recommend just using worst case, basically 5%. 5% voltage drop from any point in the system to another point, that's like the maximum allowable voltage drop. As for temperature derating factor, now that varies, as it says there, as per manufacturer instruction on battery temp correction factor. That varies dependent on the type of battery you're using and the battery manufacturer. When I gathered the data from Sonnenschein for this particular battery, the Sonnenschein at Home Lithium, they actually said that it's negligible. The temperature effect on capacity is negligible. And I'll show you in one of their documents where temperature is a factor. Go back to this one here, lithium battery data. So under the lithium battery in Connect, you've got a few of these different documents. I think it's this specifications one here. What they said that temperature does actually affect is the current. So the amount of current you can drag out of it or push into it at one time. That's what actually gets derated, not the overall capacity that's stored in it. So you can see here, as long as you're operating between 10 degrees Celsius and 30 degrees Celsius, there's no impact. But beyond that is where you start to see a derating factor on the actual current that you can charge or discharge out of the battery. So we can just put in here, as per the manufacturer, so temperature derating, we're just going to say NA as per manufacturer advice. And with regards to that next answer box, it's asking for the location minimum mean daily temperature, which also is going to be not applicable simply because the temperature factor is not having to be considered. So now that next answer box is just looking for the result of our formula that we started with. So this ETOTE-GD, I'm going to copy that into this answer box and then complete the formula. So ETOTE-GD equals EAC peak, so that's our energy requirement of the loads during the peak demand period, which was 9 kilowatt hours. Divided by our inverter efficiency, we already noted down there was 0.95, times our cable efficiency of 0.95, and we don't have to worry about the temperature as we just found out. Whereas in AT6, temperature was definitely a factor. With the lead acid battery there, there's advice in the operation manual for the lead acid battery on the formula for actually correcting the capacity due to the temperature variation. Interestingly, I think from memory, the standard temperature they use is 20 degrees Celsius for that battery, as opposed to, like, for example, we're used to with solar panels, for example, 25 degrees is usually like the baseline standard temperature. All right, so let's flow this formula on. I think 0.95 times 0.95, we do the bits in the brackets first. That's 0.9025 from there. Yes, that still works. 9 kilowatt hours divided by 0.9025 is what that ends up being. So we end up with 9.972. I'm going to turn that into watt hours, 9,972 watt hours. So see what we've done there, we've started with 9 kilowatt hours and all we've done is upgraded it to 9.9 kilowatt hours essentially to allow for these losses in transmission is basically all it is. To get 9 kilowatt hours to the loads, we need to have stored in the battery this 9.972 value we just found. Because that's how much, it's fairly significant, isn't it? Basically 972 watt hours we're going to lose due to the voltage drop and the conversion efficiency of the inverter. So that's what's going on there. That's how we're working our way backwards, and then you'll see we're going to continue to work our way backwards eventually from the battery back to the solar panels. So that we can see, okay, in order to have that 9.972 stored in the battery, how much do we need the solar panels to generate? Plus to offset the daytime loads as well. Okay, It says here in this next question, part 2, now that the energy required from the battery bank is known, determine the capacity of the battery bank. And this is that step where we convert into amp hours for lead acid batteries, and that's why we've got this formula here, which is also straight out of the textbook on that page 92. CX, where we're calculating the capacity based on the energy we just found out. And it's very similar to the power formula. You guys might recall the power formula, P equals VI, power equals volts times amps times current. And so here, what you see here is the E for energy instead of power divided by the voltage. And then, yes, we've got the depth of discharge because that impacts on voltage as well, will result in the amp hours. So you can see how amp hours is similar to amps. It's just got a time quotient in there. That's a similar sort of layout to the power formula. That's what we need to use for lead acid batteries, simply because we can't go straight to energy for lead acid batteries. We can't just go straight to watt hours or kilowatt hours, because one lead acid battery varies so significantly in its capacity that it will give you, depending on how you use it, how fast or how slow you discharge it. It just varies so much. So we can't just slap a sticker on there and say it's a 10 kilowatt hour battery. We've got to say it's a 500 amp hour battery, which then you've got to go through and calculate how much does that mean in watt hours, depending on how I discharge it. Whereas with lithium batteries, as we can see here, it's much simpler to calculate the EBAT, so the energy storage required by the battery. We just take our E tote-GD that we just calculated directly above of 9,972 watt hours, and divide it by the maximum depth of discharge. And as it says there, for DoD max, so maximum depth of discharge, consult the manufacturer data. And we did see that earlier. I don't know if anybody recalls. So I've just copied down that formula we're going to use into the answer box. So our formula is going to be our 9,972 watt hours of E tote-GD, our total energy required during the grid disconnection, divided by the DoD max. So we'll just go back and consult our battery data in Connect. And I think even just on the data sheet, yes, in this technical data on the data sheet for the Sun and Shine battery, it states there discharge depth of 80%. And I think it mentions it above as well. Yeah, just that you'll get 5,000 cycles at 80% depth of discharge. Which, if you're sizing for one cycle a day, 5,000 divided by 365, that's theoretically going to be 13.69 years. So as long as your client's happy with that sort of target, otherwise you could always go back to the manufacturer for more in-depth detail, like a cycle life graph, which there might actually be in the operation manual, I think. If you wanted to try and achieve a higher number of cycles, then you would just work out what depth of discharge you're going to work at. But I think in this case, the client is going to be happy with that. They didn't really give us much of a story on how long they want the battery to last for. But I think at this point in the game with lithium, it's best to base it on the warranty period anyway to be safe, which is only going to be 10 years anyway, at most. So 9,972 watt hours is what we want to store in the battery, divided by the 0.8 depth of discharge maximum we just found out. So 12,465 watt hours. Or 12 point, you could even round that up to just 12.5 kilowatt hours. So 9,972 watt hours was what we wanted to use out of the battery. But as we know, with pretty well every battery chemistry, you can't use 100% of that capacity. There's always going to be something in the tank. So we actually need our overall capacity of the battery to be 12.5 kilowatt hours. in order to allow for that 80% depth of discharge. Is that making sense so far? All good, I haven't lost you in the numbers at this point. Cool. So what we're going to do now is choose our battery based on what we know now so far. We've got a suggestion there, as it says, if we're using lead acid, you'd use your 10-hour capacity. And that's what comes into that whole thing I was just talking about before, where at this stage you would have calculated amp hours that you need, but then that amp hours you've got to apply it to the number of hours over which you use that battery. So a C10 reflects using that entire battery capacity in 10 hours, which is like to reflect an overnight usage, which would be typical, you know, they're in that sort of 6.5 hour range for their peak period, that sort of thing. Whereas if you were looking for a battery and you're basing it on a 100-hour capacity, like a C100, you'd get a lot more capacity out of it, but you've got to make sure you're using it sustainably, you know, over that 100 hours. In any case, it's simpler for lithium, as it says there, just use the total or nominal energy for lithium. Because we've already built in the depth of discharge of 80%, so 12.5 kilowatt hours is the total capacity we need of the battery. Remember, we've only got one to choose from, so we have a look at our data sheet again. And the total or nominal energy is 8.5 kilowatt hours of this battery that we're looking at, that one there on the screen. So we're going to obviously need 2 to achieve that 12.5 that we're after. These are going to go in parallel, 2 of these in parallel. It mentions for us on the data sheet here, just a bit further up, that you can have up to 12 of these connected in parallel. So our battery chosen is just, again, our Sonnenschein at home lithium 9.0. Number of batteries in configuration, so we've got 2 in parallel. Total nominal energy we saw there was 8.5 kilowatt hours times 2, which gives us 17. So number of days of holdover, this is to do with, okay, how often do you want to use your battery and how much of that energy that you want to use out of it does it have stored in it? So for example, with this particular client here, we're just designing for the average usage that we expect, which is that 6.5 hour peak period day on day. But if for argument's sake they said, look, we also want to make sure that there's a certain backup amount in there, or let's say Ergon changed their time of use tariff and now there's a high grid electricity cost period in the morning and in the evening, and so you've only got a shorter amount of time to charge your battery in between. In those cases, sometimes what you will do is upsize the battery so that it's got this whole, what we call holdover period. If you don't have enough time to charge the battery in between, then you upsize it to allow for holdover. Another example could be if they wanted to use it at night and then again in the morning. So rather than just sizing it for that nighttime portion, you size it for the morning as well, because obviously it's not going to charge overnight unless they're using the grid to charge it. So we don't have that in this case. They've just told us, look, we just want you to size it for the peak period. It'd be nice to have some backup if possible. What we're going to do here is just calculate and see how much backup there would be as a percentage. So we needed 12.5 kilowatt hours. So I'm just going to write this in as energy required. And then we're going to divide it by the energy supplied, I guess, of battery, which was the 17 kilowatt hours. Is that what I wanted to do, or do I want to do it the other way? 17, I should do it the other way around, sorry. Makes more sense to go energy supplied in battery minus the energy required. That allows us, it shows us how much is left over. And maybe I'll take out the equal symbols because that will get it confused. We'll just put it in brackets. So energy supplied, 17 kilowatt hours, minus the energy required of 12.5 kilowatt hours. And that gives us the 4.5 kilowatt hours that's left over. So we've got day on day, if it's used as we're expecting it to be used, we've got 4.5 kilowatt hours extra energy in the battery. So then to work out how much holdover is this, we just go that leftover 4.5 kilowatt hours divided by the required 12.5 kilowatt hours. That will give us a decimal, which will turn into a percentage. So 0.36 is what I get, or 36%. Maybe 0.36 looks better, just as it is. 0.36 days holdover. So it just means that based on what we design the system for the client, they've got a bit more than a third extra. So it's not quite enough to survive them through 2 without any charge in between. Just gives them that much extra. Okay, so we've looked at it, the different angles in terms of the overall energy that we want in our battery. Now we just want to make sure it can suit and satisfy the maximum power demand or surge demand of the loads. There's no surge demand on this site. Remember, surge is associated with loads that have an inrush current, motors, pumps, things like that. In this case, we weren't provided any information on that, so all we're dealing with is the maximum power demand. And we're given a couple of formulas there. Again, for lead acid, it's a little more involved, where we've got to use that adaptation of the power formula to convert it from power into current. Whereas for lithium, it's a bit simpler. All we do is correct the power for the losses. Again, the inverter efficiency and the cable efficiency. Because it's the same story. Like if we look at that picture again, what we're considering is the demand on the battery based on what the loads are drawing. But in between those two, we've got the cable losses and the inverter efficiency loss. So we've got to make sure that by the time the power gets from the battery to the loads, it's still got enough there. We haven't lost too much. So that's what we're doing here. Pmax, so that means the maximum power requirement of the lithium battery will be equal to the power requirement of the loads, that's what the P is for, divided by, I'm going to put some brackets in there again, divided by the efficiency of the inverter times the efficiency of the cables. So what's our power requirement of the loads? What's the peak power requirement or maximum demand? That was in our load table backup. If we scroll back a bit, remember? Yep, 7 kVA, that's right. So we just go, yep, our 7 kVA divided by, again, it's just our 0.95 times 0.95 loads, which becomes 7 divided by 0.9025. We get 7.756 kilowatt hours, or put it in watt hour format, 7,756 watt hours. Which I'm gonna round that up. I've been loving rounding things up lately, so I'm just going to make it 7.8 kilowatt hours, just so we've got simpler numbers to deal with as we work through. It's only a small rounding. So that's what we want our battery, sorry, I shouldn't be putting kilowatt hours in there. Somebody correct me. Kilowatts, isn't it, of course? This is power we're talking about now, not energy. 7.8 kilowatts. The next question is, okay, if that's what your loads require, can your battery do it? Confirm that the discharge current or discharge power capability of the battery you have chosen can handle the power demand of the loads. Check manufacturer's specifications of chosen battery. Does the battery have a maximum discharge current or discharge power capability greater than your Imax or Pmax? If so, then proceed. If not, then upsize to a suitable battery model / configuration. So again, we go back to our data here. I don't know if anybody saw it so far. And I don't think they have it. Okay, they've got an indication here, similar to what we were talking about earlier with the lead acid battery. Maximum discharge current, they mentioned there, 300 amps. But we can get more detail on this when we go to one of these other documents. Sunshine at Home lithium specifications. This one here, got a bit more detail. So the continuous output is 7 kilowatts. The peak output, which reflects that 300 amps we just saw, is 14 kilowatts for 3 seconds. And we read on down here that when in parallel, the nominal energy, peak and continuous output is multiplied by the number of units. So we've got, remember, 2 units in parallel. So we can double these values here. The 7 continuous and the 14 3 seconds. So we were after, if we go back to our assessment, 7.8. So yep, we're sweet with that. We can note in here current configuration of battery is suitable as which battery can do 7 kilowatt continuous increased by number of units in parallel, which means 14 kilowatts continuous. Okay, all good so far? Any questions or all right? Okay, now we're just checking on the charging detail. So we did touch on this earlier, and I think we noted something down. The allowable amount of time for this battery to be recharged after use In other words, before it's required to be used again, according to the client strategy. I think we sort of just noted 8 hours earlier, from 7 till 3. So we can stick with that. And that just kind of is leading into, we're going to calculate roughly how long it takes to charge. So next we want to note down the IBC max or PBC max. So that just stands for the battery charging current, the maximum battery charging current or the maximum battery charging power, depending on how it's displayed on the data. So it says consult the manufacturer data to find the battery's maximum charging current or power value and record it here. So when we go back here, it was on the data sheet. It's not on this specification sheet. This one here. It's got a max charge current of 90 amps. The intriguing thing is that you would assume if the discharge capability is increased by the number of units in parallel, you would assume that the charge current is as well, but they haven't actually said that. So, because here it told us that when in parallel, the nominal energy, peak and continuous output is multiplied by the number of units, but no mention of the charge capability. So I guess we'll just have to stick with 90 amps for now. Okay, and so now this is when we're going to do this calculation to check the charging time. Is there sufficient time to charge the battery? Assuming your charge sources are adequate to deliver the maximum charge rate of the battery, and remember not to exceed the maximum charge rate of the battery. So this is where we've got to consider both devices here, is what that's saying in the brackets there. So basically, yes, we have found that our battery can receive 90 amps. So I'll put a 90 here for our battery. But where is that coming from? Where does the 90 amps charge current come from? It comes from the multi-mode inverter, obviously. So what that, in the brackets in the question they were saying is that, look, if your multi-mode inverter can't provide that much current, then it's useless using that number. Use the highest number that the inverter can do. And also, conversely, the other way around, if your inverter can default charge higher than what the battery's maximum charge current is, make sure you limit it when you're programming it. So that's all that was getting at. So that's what we're going to check for this question here. We know that 90 amps is our max, so let's just check on our multi-mode inverter and see what it can actually do. We're looking at this SBMC 482 model. And a little further down, there is maximum charging. Here we are, right at the bottom there. Maximum charging from grid or generator. And ours is this model here, scrolling down. So it can do 156 amps into the battery. So obviously in this case, we would need to program that inverter to drop it down to 90 amps. So it's not exceeding that max charging current for the battery. So that answers the question for us as to which current value we're going to use in our formula. It'll be the 90 amps. So this formula provided here, TR, time to recharge, equals the energy we need to, or the energy we've drawn out of the battery, divided by the charging current, the maximum charging current, multiplied by the average charging voltage, multiplied by the efficiency of the battery, charge efficiency. Again, that should have some brackets around it there. And so we will fill those details into the answer box here. So what's our EBAT? How much energy are we using out of the battery? Yeah, yep, we did, didn't we? 12.5 kilowatt hours was how much we actually need to use out of the battery. or sorry, I should say that's how much capacity we need in the battery, which accounts for 20% being left in there, remember, because it's got the depth of discharge of 80% built in. The actual energy we wanted to use out of the battery was that 9972. That's how much we're actually drawing out of it to allow for the 0.8 depth of discharge. So that's our EBAT is 9972. I know it's kind of confusing how we've written EBAT there. Probably need to update that formula. But that's the actual number we want to use for this one here. EBAT, that's how much we're drawing out of it, 9972. Watt hours. And then we're just dividing it by how much we can push into it in terms of voltage and current and how efficient it is at being charged. So we've got there our 90 amps is our maximum charge current times, now average charging voltage, your voltage is always going to be higher than the battery voltage in order to charge it, but a conservative value we can use here is the nominal voltage of the battery, 54 volts. That just gives us a bit of a better, you could get it potentially from the manufacturer, what's the average charging voltage, because the voltage varies throughout the charge. Now, we can have a look at let's have a look on the PowerPoint here for a charging regime to jog your guys' memory. There's a lead acid charging regime there. You can see, okay, the solid line is the voltage and the dashed line is the charge current. So you can see how they vary throughout the stages of charge. And we will also find a lead acid, a lithium charging regime. Here we go. So again, you can see how much the voltage varies by throughout the charging stages. So you can't take straight off of there what the average charging voltage is. You would have to get it from the manufacturer. But a conservative result we can work with is the nominal voltage of the battery at 54 volts. And then we want to multiply it by the efficiency of the battery, which we recorded way back up in our little efficiency table here at 95%. So it'll go in as 0.95 into the formula. So again, I'll just do the results in the bracket first. 90 times 54 times 0.05. So you're effectively going to be pushing 4,617 watts per hour into the battery. So you just divide your required watt hours of 9972 by the amount that you can charge it with, 4617. And that gives us our result. .16 basically, around it. And that is hours. Time to recharge, 2.16 hours. Now there is a caveat with this that it mentions, and I'll show you where it comes from in the textbook. That particular formula there, where you can see it's already referenced page 135. And there's a note, it just says in bold note directly below the formula on page 135 where it says TR is the minimum recharge time because for some battery technologies the charge current is required to decrease as the battery bank is charged and the voltage rises, and therefore the time to recharge the batteries fully will be longer. And we see that reflected in that charging regime we were just looking at. See here, the charge current is only at a constant, fairly constant level through that first stage of charging. And then it begins to drop off as the voltage rises of the battery and the resistance. So, as it says, this is the very minimum recharge time. So, you wouldn't sort of let your customer bank on it. You're really just giving them an idea of the minimum amount of time it can take to recharge. And on top of that as well, right, we're dealing with a fluctuating power source if we're charging it only from solar. So you can't guarantee how much irradiance is available all the time through that. So that's why we're looking for a comfortable margin. That's why we said, okay, we've got 8 hours to charge the battery, and here we found out the minimum charge time is 2.16. So, you know, we can feel reasonably comfortable with that margin there.
Is there like a percent you have to work to? Like a value that you would say, I'd expect it to be worked out, 7% or something to be.
No, there is.
Like a rule of thumb that people work to.
There isn't one provided that I know of, no. And largely because of that whole aspect. I mean, it's different if you're charging it from the grid. You know, you can be a lot more, okay, fine, we've got 4.6 kilowatt hours, we can charge that there. So
yeah,
a lot simpler. But yeah, unfortunately with the variability of the irradiant with the solar, it makes it really difficult. And the loads too, because the loads are using out of that solar at the same time. But provided, yeah, under those conditions, if it was able to receive the 90 amps constantly at 54 volts, it's going to be minimum 2.16 because there's still that tapering off as well. It's still not going to be fully charged. All right, cool. So this is where we put together all of our... We've already started with some of these system efficiencies. We're just going to put the rest of them together. And this is, you know, out of the textbook, we dealt with this earlier in the course content as well, you know, the 3 efficiencies of the system. You can see them broken down the table here. The efficiency of using the PV generation, the efficiency of using the battery power, and thirdly, the efficiency of charging the battery bank. And under each of those 3 efficiencies, there's 2 options, you know, whether it's to do with the grid or the loads, or in terms of charging the battery bank, whether from the grid or the PV array. So again, all it is just coming back to our picture of our configuration. And I will, let me see if I can get a big fat, does the rubber get any big, no. Oh yeah, there we go. Get rid of some of that. And really all it is just tracing it through the system. So the very first efficiency was using PV generation to export to the grid. So all you've got to do is be familiar with your configuration with a picture like this and draw a line from the PV array through to the grid. So the efficiency of doing that, getting your PV energy to the grid, is going to be impacted by the number of cables it's going through, you know, the cable loss overall, as well as each of these components, your inverters that are converting the efficiency. They're going to impact on it. And so that's what we're going to build into this table here. So what we're going to see now is efficiency of cable, grid connect converter, and multi-mode inverter. And you can also follow through this again in the textbook in the efficiency chapter, which is to chapter 11. And it goes through each individual configuration from page 168. We are looking at configuration 5, which is on page 174. The blue box at the bottom of page 174, that's where we're taking all of this from. The efficiency of using PV generation to, okay, export to the grid, that's actually the second option on the page in the textbook. So it's made up of this whole, let's see if I've got another option here I can copy in. Just have to change these figures though. Our grid connect converter was 0.96, wasn't it? Our multi-mode inverter was 0.95. So that's all it is. That's just how we collate an overall efficiency by taking the individual ones and multiplying them together. All those things we've got to travel through. 0.96 by 0.95 by 0.95. We get 0.8664.
So one of the other questions on the, I can't remember which might have been 83 or something, we were saying about the efficiency of the cable between. So if you're working out this one, you're exporting to grid, you would do that, say, I think you came in at like 0.99 or something, you would do that like 3 times then, because you've got the DC wire to the inverter, then the AC between the 2 inverters, and then the cable to the main switchboard. So you just go 0.95, or, yeah, 0.95, 0.95, and then 3 lots of 0.09, 0.99. Sorry.
So you could. 2 different ways to do it, exactly right. One is that you've already designed your cables and you know what their cable loss is. So let's say, for argument's sake, yeah, you designed your PV array cable and you found that it had a 1% cable loss, so therefore the efficiency would be 0.99. And that's kind of what that question you're talking about in AT3 was getting at. You know, we've designed all our cables to have 0.99 each. The reason why that question does that, though, is just to check and test that you're looking at the right configuration. And the only way that we're able to do that is to get you to count the individual cables as well. Whereas typically you wouldn't sort of do that with a design like this. Instead, we're just giving it 0.95 overall, because that's the worst case allowance.
Yeah.
So we're just saying that whole run there is going to be 0.95, so 5% cable drop, cable loss. And then our 0.96 for our grid connect inverter. And 0.95 for our multi-mode inverter. So that's how this whole efficiency thing comes together. It's just drawing out your route of energy, where's it going from the PV array to the grid, and what's it travelling through. Combine all those together. And then, yeah, so the same thing with supplying the specified loads. It's just, we pull up a bit shorter than the previous one, because we don't have to go through the multi-mode inverter now. Because the specified loads in that whole route are before the multi-mode inverter. So it just becomes the 0.96 times 0.95. Now, you know, theoretically, it would be less than 0.95. If we've allowed 0.95 for that whole route of cable, just going now to the specified loads would be less than that. We're just being lazy and a little bit conservative, you know, to allow for it to be 0.95 as well. And then with using our battery power to export to the grid, similar thing, just drawing a line from the battery through to the main switchboard essentially. Same thing, we're just going to allow 5% for that whole cable route, and we're just travelling through the multi-mode inverter, which is 0.95, so just got 2 values of 0.95. And finally, we've just got our charging the battery bank from PV array or the grid. Same thing, we just follow, we're charging the battery bank from the PV array. You can see it's similar to this red line we've already drawn, except instead of going off to the grid through the multi-mode inverter, we just carry on to the battery. So that will look like this time, yeah, we allow for the charging efficiency of the battery. So this is the, as you'll see, this is like the most inefficient thing to do in this configuration of system because you've got so much to go through. 0.96 for the grid connect inverter, the 0.95 for the multi-mode inverter, the 0.95 for the battery, and 0.95 for the cable. Then to charge the battery from the grid, we have a little bit less to do. It's only got to come through the multi-mode inverter at 0.05. Again, the charging efficiency of the battery and the cable efficiency. So hopefully there's a lot of dicking around and, you know, detailing and that sort of thing, but I think the concept's pretty simple, yeah. Hopefully that sticks. But now we can use that detail to then continue working backwards to size the PV array. So we're going to do a very similar formula to what we did for the battery in correcting the energy or just adding in for the losses to build up the amount of energy we need. And we're going to work out what size PV array we need to produce that amount of energy by first calculating how much is required to replace the night consumption. So you see here we've got to break it into two, the nighttime consumption versus the daytime consumption, because as we've just seen in following it through the system, there's going to be different efficiencies depending on where the energy is going. So our E-tote-GD peak, so the total energy we require during grid disconnection of the peak period, we've already calculated. Back up here. It's the same as what we've got to store into the battery, the 9972. That's how much we need the battery to hold for us to use for the loads. So that's what we're going to put in down here. 9,972 watt hours. Why have I not rounded that one up yet? Might as well round it up to 10, eh? 10 kilowatt hours. I don't think that 28 watt hours is too wasteful to add in. Right, so N-bat dash charge from the PV, that's just what's the efficiency of charging the battery from the PV. We just calculated that previous table as 0.823. So it's basically 82.3% efficient, this system, at charging the battery from the PV array. So we're going to note that one in. And then we just need to calculate the EPV peak as per this formula up here. We're just taking that 10 kilowatt hours, which was our E-tote dash GD peak there, and dividing it, oops, 10, divided by that efficiency of the system, 0.823.
You might go back up to your efficiency. 1.823.
Yep.
I went ahead and did that before.
Oh, yep, this one here.
But yeah, and then,
So it's got to go from the PV array through the grid connect inverter, through the multi-mode inverter. It's got to overcome the charging efficiency of the battery. That's what the end bat is.
okay, that's the one I didn't include.
0.95, yeah, and then the cable as well. 12.15, I'm just going to round that up a little bit to 12.2 kilowatt hours. That's how much we need. So we've said that we want 10 kilowatt hours available or thereabouts. We rounded it up to 10 kilowatt hours in the battery for our loads overnight. And in order to generate that energy from the PV array and overcome the losses and getting it into there, we need to generate 12.2 kilowatt hours from the PV array. But that's just to offset that peak period energy. So next, part 2 here, we're going to determine how much energy production is needed to provide the day consumption. The same formula, just different values. What's EPV day? That's the daytime portion of PV energy we need to produce, which is equal to working out what the total grid disconnection daytime portion of energy is, divided by the system efficiency of going from the PV array to the specified loads. So our day portion, we've got to go all the way back to our load, the last time we saw the load list, to find out what a daytime, 7 a.m. to 3 p.m, how much energy they use there. And here it is, 13 kilowatt hours for the 7 a.m. to 3 p.m. period. So that's what the loads need. So we're going to put that into our question here. E-tote-GD day portion is 13 kilowatt hours. And our efficiency of supplying the specified loads from the PV array we get from our little efficiency table we just did up here. Efficiency of using PV generation to supply specified loads came up at 0.912. Carry that down here, 0.912. And we simply calculate it again the same way, 13 kilowatt hours divided by our 0.912 efficiency. Uh, 14.25, again I'm going to round up, 14.3 kilowatt hours. And then now what we're going to do, we want to know, okay, we've got two values here of energy production that we need out of the PV array. So in order to size the PV array, all we've got to do is put those two together now. So we had 12.2 kilowatt hours we need out of it to offset the peak period, which will run via the battery. And then 14.3 kilowatt hours we need to offset the daytime loads. So we are just going to add those two together at 2C-III part 3. Determine the total energy production needed from the array. EPV total, so just energy out of the PV array total, equals EPV day plus EPV night, which was the 14.3 kilowatt hours plus the 12.2. $26.5. So we want a PV array that produces 26.5 kilowatt hours. Is that, what do you reckon? Is that surprising? Did you think it'd be that much, or be less, or more, or?
Maybe a little bit more, but
Yep. Yeah. And bearing in mind too that we're not offsetting the nighttime consumption, so we kind of aren't doing the whole 24-hour period. We're just doing the daytime and the peak period.
if you've got spare space in the battery, you could just oversize the system anyway to produce more electricity nighttime anyway, wouldn't you?
You could, that's right.
You wouldn't really aim for a system that produces that now. You'd be going for a bit more.
You could. You've got all these design decisions to make, hey, with the client. Because see how we had to, one battery wasn't enough, so we had to go to 2 batteries, which gives us an extra 4.5 kilowatt hours. Still not quite enough for the nighttime period, which was, what was the nighttime? So close. 5 kilowatt hours. It's pretty close, isn't it? Probably yeah. Half a kilowatt hour, you'd probably just, yeah, it's close enough. It's going to go one way or the other from day to day anyway. So
it uses one battery. What are you saying?
no, that's for the 2. So
Oh, okay, yeah.
remember we worked out,
Yeah.
because we've now sized the PV array to cover all the daytime usage of 13 kilowatt hours, bearing in mind, of course, that we can only ever work with averages, because one day you'll have a rainy day and it'll all go out the window anyway. And then we covered the PV array and the battery sizing to cover the peak period, but we didn't size anything for the night period, but we do have 4.5 kilowatt hours excess battery storage, and it's a good point that Jack raises, because we haven't sized the PV array to provide that extra 4.5 kilowatt hours. So what that means is that what would happen is at some point you'd use the grid, or you just have a day, a longer summer day where you get a bit more excess solar and your battery gets charged up. But from day to day, we haven't designed for that 4.5 kilowatt hours to be used regularly. So you certainly could. You could add that extra, nighttime 5 kilowatt hours into your PV array sizing. Plus the fact that, exactly as you say, in most cases, especially with our STC scheme in Australia, you just oversize it, And that'll become more clear as well as we move on here with determining the actual power rating and number of panels in our array. So currently we've just got the energy output requirement of 26, wasn't it? 26.5 kilowatt hours. And now we're going to walk that backwards. So this is where, you guys will be familiar with, in terms of grid connect design, we go, okay, here's a certain size PV array, and usually it is limited by, I guess residentially speaking anyway, but there's usually grid limits, like grid allowance limits that limit the size of our PV array. For example, like I said before, single phase is 10 kilowatts total, limited to 5 kilowatt export. 3 phase is typically, well, it varies, but 5 kilowatt per phase. And then you start to get into commercial. Your next sort of obstacle is 30 kilowatts before you need grid protection limits into the next range. So all that sort of thing usually tips on to deciding, that's why all the systems we see on the ads on TV is 6.6 kilowatts, because that's the most common residential system. So in those cases, you just are giving the client, here's your size system, here's the energy it'll put out. But now we're going backwards, we're going, this is how much energy we need out of the system, and we'll work out what size. So 2C Part 4 is determine the array size in power rating, and this is our formula. So the total energy in PV is made up of the power rating of the array times the correction factor or derating factor of the PV times the peak sun hours. So we're going to transpose that formula in a minute, because the value we're actually after is the rating, P rated. That's what we don't know yet. So let's work out our derating factor for the PV array. as it says, we assume the nominal rule of thumb 5% loss for dirt. Manufacturer's tolerance. This is one that's often overlooked. What is it? Remember, with regards to the manufacturer of the solar panel, they are trying to manufacture for us a 295 watt panel, but there are certain tolerances on every manufacturing line. You can never perfectly clone one product after the other. There's always just tolerances one to the other. So they have this manufacturer's tolerance where it could be up to 3 to 5 watts or thereabouts difference from one panel to the next. But the way they manage that these days is they provide us the minimum. So when we buy a 295 watt panel, if it's got a positive tolerance only, which typically they mostly do these days, it means that it performs at 295 watts at STC conditions minimum, and up to typically extra 5 watts, up to 300 watts. Because then the next power class they'll sell you is a 300 watt panel, and it'll operate up to 305, anywhere in between there. So, and we'll see that confirmed here when we look on the QCell data sheet. And it's right in here, minimum, see here under the electrical characteristics, minimum performance at standard test conditions, STC, is a power tolerance of plus 5 watts and minus 0 watts. So it means if you're buying this 285 watt module here, you can expect it under STC conditions, of course, to operate anywhere from 285 up to 290, but not below 285. That's our manufacturer's tolerance. So because there's no negative tolerance, there's positive only, we just negate it. We don't have to allow for a loss there. So you could just put that in as 1, or even not applicable. But a factor of 1 doesn't change the end result, obviously. Oh yeah, that's meant to go in there. Positive tolerance only. E.g., what we saw there was plus 5 watts / minus 0 watts. What else we got? Okay, so we want to work out our temperature correction factor. As per the PV data sheet, we'll find the temperature coefficient for PMP. So if we go back to our data sheet, look for the temperature coefficients. They're a little bit further down on our solar panel data sheet. And there they are. You've always got temperature coefficient for short circuit current, temperature coefficient of power at maximum power point, which is what we're after. Negative 0.39. It's got percent per degrees Kelvin there, but it's the same increments for degrees Celsius. No conversion required. So negative 0.39%. That's our answer here for the PMP temperature coefficient. Negative 0.39%. So all that tells us is that for every rise in temperature in degrees Celsius above the 25 degrees standard testing temperature, we will lose 0.39%, so a bit less than 0.5% of our power. Now we're given our cell temperature here for the site. The lowest is 5 degrees and the highest is 80 degrees with an average of 67 degrees during the daytime. So that will come in handy in a moment when we do the rest of that power temperature correction formula. And our peak sun hours, we already noted that down at question 1B III, which was 5.4. Alright, so we can carry on, calculate the temperature correction factor for the PV modules. This formula here, you guys will recall, like it was yesterday, from Grid Connect Design. F-temp, so the temperature correction factor equals 1. Why does it start with 1? Because 1 is a whole number, non-derated yet. We're wanting to derate it. So 1 plus, and then in the brackets, the square brackets, the y is for our temperature coefficient. The key to note here, because this formula is copied directly out of that reference there, clause 3.4.3.9, from AS459.2, which, if you're wondering what that standard is, that's for standalone power systems. That's just where it was first introduced into the solar industry, that formula. The key to make this formula work correctly, and you should know at the end of it anyway if you've got it right or wrong, because it's a derating factor, which means you'd have a number less than 1. If you get a number more than 1, then something's gone wrong. The temperature is not going to add power to the output of our panel, it's going to detract from it. And the way that you can get that wrong is as to whether or not you carry the negative for that temperature coefficient, that Y. And I'll show you. We'll put it into this box here. That's our formula we're going to carry on. F10 equals 1 plus. Now our Y that we're going to put in here is our temperature coefficient, our negative 0.39%. But we're just going to put it in. Now we've got to put it in as a decimal, as it tells us here. Y equals PMP, temp coefficient, as a decimal. So as a decimal, because it was a percentage, 0.39%, to turn it into a decimal, we divide by 100. So it becomes 0.0039 as a decimal. Does that make sense? I might just type it in here. So convert.
I would have thought that convert it to volt.
No, that'll be later when we are doing our strings. So this year, what we're doing here, we're not correcting voltage, we're correcting power. Yeah, but I know what you're thinking of, and we'll do that later.
Yeah.
So convert temperature coefficient from percentage to decimal equals, okay, so it's negative 0.39% divided by 100 equals negative 0.0039. And I should write it as divided by 100%, and that takes the percentage out. But when we put that temperature coefficient into the formula, we drop the negative. The only reason being because to make the formula work, because there's a plus in there. 1 plus the square brackets. If you wrote it as 1 negative, hang on a minute, I'm shooting off at the mouth. Rewind that. That's why the plus is in there. It's okay. Because that's going to be a negative. Yes, we carry the negative. I was recalling another day at a different time. Forget about that. We carry the negative down. 1 plus our temperature coefficient, which is negative 0.0039 now in a decimal format, multiplied by, okay, in the brackets we had there T cell minus TSTC. T cell is the cell temperature of our actual solar cells in the solar panel, which was given to us back up here. 80 degrees is our maximum, 5 degrees is our minimum, and our average is 67. Which one of those are we going to use? So we are going to use the average. The reason being, here we're correcting power for all time, all year round. And so what we're doing is just grabbing the average daytime temperature of the cells. Now 67 is pretty high, but that's because if you have a look in the CEC guidelines, Clean Energy Council guidelines, you'll notice in the design guidelines with no battery storage, it's focusing on the solar panels. And they give you nominal temperature values to add on to ambient, dependent on how your solar panel is installed. If you install your solar panel up on a ground mount, that's the optimum airflow and ventilation you can get for a solar panel. They recommend adding 25 degrees over and above the ambient temperature to those solar panels. That's how hot you can expect them to get in the middle of the day. If you're installing now on a tilt frame on a roof, okay, you've got a bit less ventilation, you add 30 degrees over and above ambient temperature for your expected daytime cell temperature. Because obviously the cells are inside the panel, they get hotter than the ambient air. And then the hottest is if it's flush mount, which the majority of our roof mount systems are, parallel to the roof, flush mount. Those you add 35 degrees to. So you can see how you end up with an average cell temperature of 67 here. The 67 minus 35 is only 32, and we're in Cairns. So 32 is probably a reasonable daytime average ambient temperature. Yeah, sure. Right, so we're in the middle of this F-temp formula. And we're just about to put our cell temperature in. We determined that we're using this 67 degree temperature because it is the average throughout the year. So we're derating power here on average throughout the whole year. We're not targeting a specific time of year or anything like that, whereas, like we mentioned here before, that when it comes to voltage, we do a very similar formula for correcting the voltage, and that's when we look at the extremes, because we don't want the inverter to be damaged, for example, if our voltage goes too high, or for it to basically contravene standards, because we're not allowed to have it, over a certain voltage. And then the other end of the thing is that if the voltage goes too low, the inverter can shut down. So that's why we use extremes in that case. So we've got our T cell of 67 degrees minus our SDC temperature, which is always 25. And now we can complete the formula. .7 minus 25 is 42. So 1 plus minus simply ends up being minus. So 1 minus 0.1638. The result becomes 0.8362. So it simply means that our panels are 83.62% efficient on average due to temperature alone. So that's our F-temp. Just another one of those losses that is poorly understood, particularly in the lay market. Like, when people sort of expect that a 300 watt panel is going to put out 300 watts, and so if I've got 20 of them, okay, at 6 kilowatts, why don't I see 6 kilowatts on the screen in my inverter type thing? After shading, temperature is generally the most significant loss, especially here in Australia. So now we're going to combine all the PV module correction factors that we've just looked at, which is just dirt, manufacturer's tolerance, and temperature. We saw that manufacturer's tolerance is no longer in play for this manufacturer at least. It was positive tolerance only, so we're just combining our dirt of 0.95 times our temperature we just found was 0.8362. And that's our FPV derate. Those two combined. So that was the last factor we needed. Now, in order to be able to work out, okay, given the amount of energy we need and the losses associated with the PV and the peak sun hours we receive, what size PV array are we going to need to push out that amount of energy? And that's this next formula. So we had an energy requirement. EPV total was 26 something. Yep, 26.5. That's our EPV total divided by the FPV rate we just calculated as 0.7944 multiplied by our peak sun hour value we've been using of 5.4. .2 kilowatt hours. Sorry, kilowatts. That's the rating of our array that we need. So then the next question to GCwB Part 5 is just, given that P-rated value that we just calculated, how many of your chosen solar PV modules will be required in the PV array? So we're going to go probably with the 295, with the Q cells we've been looking at. Probably with the 295s. Where are they? Zoomed in too much. Simply because they're the biggest, I think, that are on offer. 285, 290, 295. So if we take our 6.2 kilowatts divided by our 295 per panel, I get 21.017, and it's funny because I just rounded up that 6.2, so I was like, I wonder, 6.175, does that get us under?
Maybe get down a little bit.
Looks like it does. Okay. 6,177.5 divided by 295. Yes, I shouldn't have rounded it. I get too excited with my rounding up. I'm going to get rid of that. Divide it by that value instead. .94. So yeah, this one you have to round up because you can't use 20.94 modules. Therefore, 21 modules. That's our minimum. The interesting thing here, though, too, is that that we've worked that out as our minimum number of modules. Anything that we do to put a kink in the hose, so to speak, from here is going to impact that, right? In terms of, I assume, most people would look at that and go, oh yeah, just under 6.2 kilowatts. We'll whack that on a 5 kilowatt inverter, especially if it's, single phase and all that sort of thing. But straight away, there's a kink in the hose, isn't it? A 5 kilowatt inverter. Yes, there's going to be some losses between the 6.2 kilowatts down to the 5 kilowatt, but you can pretty much bet on the fact, depending on the layout of your panels, especially if they're all on one tilt and orientation, at some point your inverter is going to be capping that excess input from the PV array. So just something to bear in mind. And that's where we're up to now, is matching our PV array to our MPPT. Using the generic term MPPT because it could be a charge controller or it could be a grid connect inverter. And that's why down here it's asking us now to put in all of the specs, and it says from the MPPT, whether it's a controller or an inverter. State the following. So we've already chosen that we want a Fronius Primo for earlier on, and now it's just a case of what size. So we've got, in the Primo family, we've got anything up to 8.2. I've just made mention of something there that could make us want to go a bit larger than 5. Like, based on what I was just saying there, you'd want to at least go with a 6 kilowatt, because there's less of a kink in the hose. But then the other thing we've got to consider is that with grid connected, we can only have 10 kilowatt total inverter capacity. We've got an AC coupled system here, 2 inverters. When you go with your multi-mode inverters, if we have a look back at that one, that's electronic, when it comes to your grid approval, it's based on this, on your continuous rating.
You can just choke and pipe that.
So you're talking about export limiting?
Yeah, export limit. You can do whatever you want.
So, but this is total AC capacity. And it needs to be limited down to 5 kilowatts, yeah. So it brings in an interesting, in this particular scenario, an interesting factor here where you can see here that the inverter that I was talking about using was this SPM C482 multi-mode inverter, because it satisfies, you know, at 7.5 kilowatts continuous, 8 kilowatts for 60 minutes. It meets that max demand value we need. But at 7.5 kilowatts continuous, it only leaves us 2.5 kilowatts for our Fronius inverter. And the same was true with the Fronius inverter. We're looking at wanting at least a 6, it only leaves us 4 for the multi-mode inverter. So you're kind of at a bit of a crossroads here where either we've got to compromise and go 5 each for these two and tell the client, okay, see how that next, this is our other option for a 48 volts electronic, and it has a continuous rating of 5 kilowatts. We could couple that with a 5 kilowatt Fronius inverter. It just means that, as you can see there, we're kind of just coming under their max demand of 7 kilowatts. We can do it for 30 minutes, but no longer than 30 minutes. So this is where you'd sort of be saying to your client, you've got 2 options. One is just be willing to kind of come under that, and you know your budget's going to be okay and stuff like that. Or what else could you suggest? Because this is where you're kind of feeling out your customer, aren't you? Like how much they got to spend, basically. Because another option could be upgrade their mains.
Three-phase.
It's a 3-phase, yeah.
I've done that in our company.
Because, I mean, you never know. We're just going on a simulated environment here. Like, it could be that they have got a 20-year-old ducted aircon system and they're like, well, we were considering putting a 3-phase ducted air on, you know. So if there were any other factors that could lead you that way, then sweet. We won't bother with that for this. We'll go the other way just to keep us all on the same page. But it's just one of those things, where you realise, oh, there's a limitation there.
So what's the other 10 kilowatt system? You can only have 10 kilowatts of AC output in one thing.
Yeah.
Even if you, when you're like retrofitting, you can write as there's an existing system there, and you choke them both, so the export limit anyway, it doesn't matter.
So when you say write, what are you writing on?
Like in the system, you write, like we don't write obviously, you just program it to say that the existing system, the 10 kilowatt inverter there, so it knows, and then you set both the export limits down on 5 kilowatts anyway.
Yeah.
So is it illegal to have more than 10 kilowatts of AC output in a household?
So this is coming to your, because you know, like Energex or Ergon or whoever regulate the grid, so that's their infrastructure that we're connecting to.
Yeah.
And yeah, so their rulings that comes under the connection standard. So if you go, you can search either Energex or Ergon, they're both under Energy Queensland,
Yeah.
and they have the connection standards on their website. Standard for low voltage embedded generator connections, that's what EG is. This here will be the latest one. So yeah, as you can see, they're both together under Energy Queensland. Effective from 18th of December 2021. So this is fixed embedded generating system parallel. Standard covers inverters from 30 kVA to 1500 kVA. So that's actually above 30. That's not the one we want. The other one we want is micro. Oh, here we go. Small IES connections. Standard for small IES connections also from 18th December 2021. And somewhere in here, did it tell us there? Somewhere it should have the sizing. Standard plus air connection, the total system, so that's saying all equal to 10 kVA per phase. And then it goes through like single phase and three phase as well a bit later on in terms of scale. Technical requirements, following subcategories. So single phase small IS fixed EG connection can be up to and equal to 10 kVA.
That's it. Yeah.
Yeah. So this comes into, like, this is before even going on site and installing, obviously,
Yeah.
putting in your application to them.
Yeah.
So anything that gets connected to the network, you just got to submit an application and then a work request afterwards.
Yeah.
Yeah.
So if someone's got, let's say, 2 5 kilowatt equivalent converters on a single phase plant,
Yep.
what are the options then?
Replace them. If you want to add a battery, replace one or both. No, can't increase the AC connection. I mean, apart from getting really creative, which is like, so everything here that Energex regulate or ergon is to do with grid connection. Something you could do is an off-grid system that functions like a UPS behind a break before make switch. So as long as it can never be in parallel with the grid, it's fine.
Yeah.
So again, it comes down to your client, but you could install a system on their site that goes, okay, it's a solar and battery system or whatever, and it provides the loads maybe as a preference, if that's the way they want to go. And when it gets too low, you know, the battery signals the inverter and it switches off. You could have an automatic transfer switch that switches them back to the grid, something like that. There's application for that.
So you couldn't have like a 10 kilowatt or 8 kilowatt inverter and then retrofit a 10 kilowatt battery inverter.
No, well then you'd be 18 kilowatts, yeah.
Yeah.
And see, that's one of the arguments that points us back towards DC coupling, because with DC coupling you can add batteries on without increasing the inverter AC capacity. Such as like when we go back to our configurations. If you've got one inverter, for example, like this, configuration 1, you know, you can add as many batteries on as you want as whatever that inverter can handle, and you're not increasing the AC capacity of the switchboard.
If you're retrofitting it, you can run the level, sure.
Yeah, because if you're retrofitting and you don't already have that hybrid inverter, you'd have to replace it, with whatever the existing inverter is.
Replace stuff. Replace inverters with them, take one array, that's always
Exactly.
shit out.
Yeah, and that's the whole benefit of AC coupling. You don't have to touch anything else, but when you're replacing the inverter that's connected to an existing array, exactly right, you've got to then bring up to standard certain aspects of the array.
What's the most common system being studio and simple? This is that.
Yeah, well, there's always other nuances too, what people prefer to deal with, manufacturers-wise. Like a lot of people, in fact, before Tesla, a lot of people say this, and I don't know whether it's true or not, but the reasoning why Energex increased. Like it was just a blanket 5 kilowatts per phase. So single phase was just 5 kilowatts. But see, everybody had a 5 kilowatt Grid Connect solar system on. And then Tesla were one of the early ones with Powerwall 2 to bring out, a retrofit product, really. And so Energex, they actually increased the allowance at that time for up to 10 kilowatts connected, but only 5 kilowatt export still. So they are a very neat option for that. And there's a lot of other variations too of, an inverter and battery all in one module type thing. Redback is another one, but that is a hybrid inverter, so you could actually attach more solar to it as well. Yeah.
LG get a battery inverter, don't they? Pretty sure.
Well, I've only just noticed recently that they brought out an inverter, which is a rebranded GoodWe.
Okay.
Yeah. I haven't seen whether they do it in one component or not. ABB have got one.
Oh yeah, that's what I might be thinking of.
QCell even have got one as well. There's a fair few out there, yeah.
So if you've got like, say, configuration 5, you're trying to monitor your system, is there an easy way to do it? It's just to have that config 1 and just put 2 multi-mode inverters on. Because like for this one, for instance, you've got 2 different brands of inverter and it's easy to keep an eye on everything if you're looking at one system.
Yeah.
So do you do that? Is that something that people do? Put 2 multi-mode inverters on, 5 kilowatts?
Possibly. I've never done it myself. I know that it becomes a problem when they're running in backup, but I don't know whether, I presume they can run in parallel okay with the grid. Yeah. But yeah, I see what you're getting at, because that gives you the capability to be able to increase both PV array and battery.
Yeah. And I just assume that it would be an easy way to install it. I would assume that
Yep.
somebody wants to try and buy 2 of their products.
Yeah. But at the same time, why 2 instead of 1? Like as we saw earlier, you've got the Solar Edge, the SE10000, which pretty much takes up all of that grid AC capacity for single phase anyway. The only reason why we've got 2 in configuration 5 is because one's a solar inverter and one's a multi-mode inverter, to allow the larger power output from the multi-mode inverter.
Which now is going to be trumped anyway.
Yeah.
You're going to have to pick a low one.
Yeah, that's right. And really, we've been corralled into it because of the options we've got available on Connect. Like, we could have gone with, as we saw, the Solar Edge Energy Hub for configuration 1, for example. Yeah. So yeah, it's just interesting things to be aware of anyway in the process. So we'll end up just going like a Fronius Primo 5.0 and we'll stick with the 5 kilowatt SP Pro. So I'm just going to pull all the data off of the Fronius data sheet. Which I think most people are using the SCs now. Do you use Fronius much? The SC, Super Current, or whatever it's called, Superior Current, I don't know what it stands for. They tend to be the most popular. But all the input specs are pretty similar. 80 to 1000 on the operating voltage.
I know you can get the only difference is we had a company was one was like an international one and one wasn't. So the input currents were different.
Yep. Just like you see here, so the Primo 5.0-1 was international, so you got 12 amps for the input current as opposed to 18 amps on the Australian or SC. But the difference with the Australian one was this 4.6. See the nominal output, the power output was 4.6, whereas the SC is now 5,000. There was a period of time, particularly back when the solar bonus scheme was around, that there were limitations in Australia. I don't know if it was just Queensland, I presume it was more than Queensland. They wanted maximum 4.6. They were keeping it under 5 kilowatt of the nominal rating for some reason. Yeah, so now if you're doing a retrofit for those ones, it's very difficult. So I don't even know whether Fronius, they're pretty rare now, those Oz ones. I don't know how many of them in the country. ABB, I had to do it at my place because I had a 4.6 because it was from 2011. And I've got the solar bonus scheme, and you don't want to negate that by putting a larger inverter capacity on there. Right, so we'll chuck those specs in here. Max input voltage is 1000 volts, even though we'd cap it at 600 for the residential. MPPT operating voltage, similar thing, it's 80 to 800. Max power input was, I think it was 7.5 kilowatts. Yep, for the 5. Max input current. Now, we've got there 18 and 27. So 18 amps is max input current, and 27 amps is short circuit current. So you think about operating and short circuit. So the 27 amp one is the one that's going to damage the inverter if you exceed it. The 18 amps is what it can actually use. So you can push more than 18 amps, anything up to 27, but it's only going to be able to convert 18 amps per MPPT. Nominal rated AC output power, I'm pretty sure it's 5,000, wasn't it? Yep. Then our solar module spec. So from our Q cell, we've got 295's 9.7 short circuit current. We had VOC of 39.48. And 32.19. Voltage, temperature coefficient is about 0.28. Down here. 0.28. So you can see there out of those two temperature coefficients that the one for power and maximum power is the larger one, so you lose more when the circuit's under load. That's what maximum power means, the circuit's under load. Voltage at open circuit, obviously the circuit's open, so there's no load. We can use that temperature coefficient for that condition of the circuit being open. But whenever it's closed, under load, we're using that one, the larger one of the two. So if you wanted to simplify it, you just use that one in both cases. So we've got to calculate our minimum number of modules in series, our maximum number of modules in series, and our maximum number of total modules in the PV array. So some working space there you can use if you like to do it longhand, otherwise, and then finally choose our actual PV wiring string configuration. Otherwise, we've got this spreadsheet tool in here, a couple pages down, which is a handy one. I'll take you through it. So our MPPT voltage input, whilst it was 800 for the Fronius, unless we're going to satisfy the requirements to achieve, be able to use 1000 volts now, we're going to have to stick to 600 as per that yellow asterisk, just remembering it. Max input is 600 for residential, put 600 in there, as well as for the MPPT max. Now MPPT minimum voltage was 80 volts, so we're just carrying down the values from above that we just recorded in. 2.17, I think it was, for VMP. – 32.19, sorry. Now our temperatures, this is where we use those extreme temperatures that we saw earlier, the coldest being 5 degrees. And the hottest was 80. So we've just put in the first column the MPPT voltage input from the specs, second column the module voltage output, so module being solar panel, output from its specs, and then third column is T ambient, so the ambient temperature, not the cell temperature, but the ambient temperature. So 5 degrees was given to us as a cell temperature as the coldest. Now they're the same. Ambient and cell temperature at coldest is the same. The theory there, and you'll see it in this next column where it says T cell, so temperature of the cell at noon, is equal to the ambient temperature plus one of these nominal values. Remember we talked about it earlier, 25, 30 or 35, depending on how you've installed your panel. Whereas dawn, you can see here, is simply equal to Tm, ambient temperature, because the theory there is that the sun's just come up at the point, like there's just light hit the panels at the point where they start to generate voltage, and they have not heated up yet. So again, that's going to be 5 degrees for cell temperature for the first two rows, which is the same as coldest dawn. Whereas hottest noon we saw was 80 degrees for the cell temperature. If you wanted to, I mean, we could pretty well skip that previous box because we don't need the ambient temperature because we've already got the cell temperature given to us for 80 degrees Celsius, but you could backwards calculate it by going the 80 degrees minus the 35 degrees that we're allowing for a flush mounted PV panel. So we get 45 is basically the hottest noon, which is probably pretty realistic for Cairns. Is that making sense so far, what we've put in? Just banging in the numbers. And then the spreadsheet's going to guide us through doing the calculations. So column 5, we want to put in T diff to STC, so temperature difference to STC. So take our cell temperature we just put in that column 4 and minus off of it 25 degrees. So for example, 5 minus 25, our result is going to be minus 20. Then for our hottest noon, it's going to be 80 degrees minus 25. It's going to be 55. Next, we're going to put in the temperature coefficient. This is the most difficult bit of the whole spreadsheet because it wants it in the format of volts per degree C. The problem is, like we recorded earlier, and all the solar panel manufacturers, they give it to you not in the format of volts per degree C, but rather in a percentage. So what we've got to do is convert it into volts by following this, where that yellow hash, highlighted hash is down the bottom here. It shows us how to do it, to convert from percentage to volts. And this is an example here. If these were your values, then the way you would do it is simply convert your temperature coefficient from percentage into decimal first, and then multiply it by the voltage you're working with. So, first row here, we're working with our VOC of the panel, 39.48. So we need our VOC temperature coefficient, which we recorded just up here before, remember. VOC temp coefficient is negative 0.28%. So that one there, we need to convert to a decimal, which is simply divide by 100. Convert to, it's going to be negative 0.0028. And then multiply it by our VOC voltage of 39.48. That will give us the result in volts per degree C. Point 11 volts per degree Celsius, and that's a negative. Don't forget to carry a negative. That's like the hardest bit of this whole thing. But hopefully it makes sense. All we've done is taken the manufacturer's given us the percentage. They tell us you're going to lose voltage as your temperature increases by this percentage, and we've just backwards calculated it to turn it into a voltage. How much volts is that? How many volts is that? And it comes out as 0.11 volts for every 1 degree Celsius that we increase above 25. So the next row down is going to be different, because now we're VMP. We're under load VMP. That first one was VOC, so we want to use this time the temperature coefficient for power at maximum power. It's slightly more. You can see negative 0.39. Bit of a bigger quotient than negative 0.28. So we convert it to a decimal. Negative 0.0039. Times the voltage we're working with this time in the same row, the VMP of 32.19. And we'll find out what 0.39% of 32.19 is. Point 12.5 volts per degrees Celsius. So you lose slightly more of your voltage at maximum power than your voltage at open circuit. And we can carry that down to the final row as well, because both of those two bottom rows deal with the MPPT voltage. Any questions on that? Because I know that's sort of the bit that usually hangs people up. So far, so good. Cool. Right, so the next column's asking us now to find the module voltage difference, which means the spec sheet told us what to expect out of our module voltage, out of our module in terms of voltage at STC, at standard test conditions. But the reality is we are in a different situation than standard test conditions. We have a different temperature. So we want to know what our actual voltage is going to be for that scenario. So it tells us how to achieve it. Just go column 5 times column 6. So we've got negative 20 degrees Celsius is column 5 for the top row, times our result out of column 6 was negative 0.11 volts per degree C. And remember, multiplying two negatives together will give us a positive. .2 volts. That's how much our module is going to increase by, 2.2 volts, because it's a positive value. Do the same for the next bottom two rows. Actually, a negative 2, shouldn't it? Up to my negative. .125 times 25. But then it changes with the very bottom row in terms of, we don't have a negative coming from column 5. We've got 55 degrees, which is a positive, 55 degrees Celsius, multiplied by negative, sorry, again, I didn't have it there it is, negative 0.125. So multiplying a positive by negative will end up in a negative result, unlike the top two. Negative 6.87 volts. And that makes sense because what we know from our theory with our solar panels that temperature and voltage are reverse. So when we're going to the coldest temperature, that means temperature's dropping, we're expecting the voltage to be increasing. And that's what we've got happening in the first two rows because they both relate to coldest dawn. Therefore, we've increased voltage by 2 odd volts. Whereas in the bottom row, we're dealing with hottest noon, so therefore we've lost voltage by that much. So we just add that on to our original STC module voltage in column 8. It says module voltage at T cell, so at the cell temperature that we've calculated it at, equals column 2 plus column 7. So we just go back here, 39.48 was column 2. Copy that into column 8 plus column 7. Oops, typo there. .68. That's what our panel's actually going to be producing, 41.68 volts at 5 degrees Celsius. Same process for the others, column 2, 32.19 plus column 7. And once more for the bottom row, we get our column 2, 32.19. Plus our column 7, which of course in this case is a negative.
What's the voltage drop percentage mean?
Yeah, so because in this bottom row, what we're trying to work out is what is the minimum, absolute minimum number of modules we can have to ensure the inverter continues to operate at above its 80 volt minimum. So, whilst we correct voltage at the module, there's also voltage drop from that module along the cable to the inverter to allow for So 32.19 minus 6.87 gives us 25.32. Now what voltage drop to allow for here is up to you. Again, it's sort of, have we already designed the cable or not? And I just, for argument's sake here, I just make it worst case, which is 3% is the maximum allowable voltage drop from the furthest module to your inverter. So I just go times 0.97 efficiency, which allows for a 3% loss. .5 volts. So then what we do in column 9, as it tells us, divide column 1 by column 8. So column 1 was our input voltage. For the first row it was 600 volts, was our maximum. And we simply divide that by our corrected voltage for our modules. From column 8. And that will tell us the result, the number of modules. .39. And then the final, you'll see in the final column there, to find out the modules per string, of course we've got to round it. And we've got to work out whether round up or round down. Of course, when we're trying to stay below a maximum, we need to round down. So therefore, that one is a result of 14. This one. So hopefully that's all making sense so far. So yeah, what we take from that is that whilst we can have 17, for example, not to exceed the upper limit of our maximum power point tracker, it wouldn't work for us because we can't have more than 14 before we exceed the open circuit voltage input. So our maximum we can see is 14 per string, and our minimum is 4. So that's our voltage sorted out. The next step is to consider current. As it says here, step 2, use current to determine max number of strings. And we've got some guidance there. Max number of strings equals maximum MPPT input current divided by the module short circuit current. So pretty straightforward there. And we recorded those values before in that previous table, which was 18 input current and 27 amps short circuit current. So we can actually kind of consider both in that so max input current of 18 amps divided by our operating current of the panel, which was 9.17, I think. Yeah. 9.17 amps is our current at maximum power point. So this gives us an idea of usability. So as you can see, it comes up just under 2, 1.96, suggesting we can only have one string. But this is just, put in brackets there, usable. So it's actually, that's very okay. The other thing to be aware of is max short circuit current. This is the more concerning one that we have to be under. Ensure we don't have any damage. And that was, say it was 27? Where did we put that? Yeah, 27. So max short circuit current was 27 amps divided by the short circuit current per the module, which was 9.7 amps. So 2.7. 2.7 strings max, and that will avoid us damaging the inverter. And that maximum input current usable is actually very close to ideal. 1.96 coming in just under 2 strings. So it just means with the 2 strings, if they are operating at maximum current, you're going to lose a tiny bit. It's going to have a little bit shaved off it by the input of the inverter. Two strings will have a very small amount limited inverter.
Yeah. 18 divided by 9.7.
9.17. This one here.
Yeah.
Oh, sorry. Did I do something wrong there? Sorry. Yeah, 1.96. Yeah. In terms of what it's saying is because they're 9.17 amp output, you could only fit 1.96 of them into the 18 amps, is what it's saying. So we're nudging just above that by pushing 2 into it, which means we're just going to lose a little bit of the current, yeah. So yeah, most inverters have got these windows on their data sheet of both those two levels of current because, you know, similar to the panels, they have an operating current and a short circuit current capability. And then as far as power goes, well, we know that from our Fronius Primo, its maximum PV array power was 7.5 kilowatts. And we're just going to divide that by the power and SCC rating of the module, which of course is 295 watts. So I should put that in the right format and make it 7,500 watts rather than 7.5 kilowatts. $25 modules maximum. So that really leads us to what sort of configuration we're going to go with. If we're going to have 25 in total, maximum strings of 14, minimum strings of 4, it's a fair bit of flexibility there. I guess arguably, obviously without having the explicit limitation of the roof space, we could just split it 13 and 12, a string of 13 and a string of 12. One on each MPPT. Alright, on to our multi-mode inverter. So as far as designing it, we've already covered really most of this. It's just going to be putting the details in. One thing that hasn't been raised so far is this, which unfortunately we're not going to be able to achieve anyway, but it's just an industry recommendation to apply a 10% safety factor to the power output capability of your multi-mode inverter. So as it says, in other words, just multiply by 1.1, and there's a reference there to a section in the textbook where it talks about that. So this would mean that our 7 kVA safety factor times 1.1 obviously would be 7.7 kVA, but as discussed, we're sort of limited by our allowable capacity anyway with connection to the grid. So check to see that the battery voltage is correct. We did already check that, if you recall. We looked at the data sheet for the lithium battery, it was 54 volts. And now, with regards to this electronic, the model we're going to be going for is the SPMC 481. And yeah, we can verify with it a bit further down here. The rated DC input is 48 volts with a range of 40 to 68 volts. So that will suit also our nominal 54 volt battery, which is also further verified by on the battery data sheet that it references this electronic SPMC 481 here as a suitable inverter. So that's our other verification there. So yes, the battery voltage is correct. So the next question, the inverter can handle the max demand times 1.1. If not, what is your strategy to deal with this issue? So here, we've just got a detail like due to the NSP grid allowance of max 10 kilowatt connection. A compromise has to be achieved here. Slightly less max demand capability. So what is it? I'll just verify again on this data sheet for the inverter. 5 kilowatt continuous. Okay, so we can do 7 kilowatts for 30 minutes. So it's close. Like they could have a half-hour max demand just without the safety margin. So we'll just note that down. 7 kilowatts for 30 minutes. Customer has been advised. So our final selection then is this electronic SPMC 481. Got another spot here. It seems like a bit of a double up, but it's this whole process of now completing the design, where it's just asking us to now just finally select and justify the configuration we've chosen. So something along the lines of we're proceeding with configuration 5 due to the accessible products as this well. Do the most effective job of the customer's design strategy. Determine location for components. It's just this whole thing of we're revisiting what we planned in the beginning, and you just note down any changes, but probably you don't have any changes, so you can simply just copy paste into this one what you had earlier on with regards to locations of all your equipment. That brings us to 2F. Size the cabling, isolation and protection. Size all of the required cabling, isolation and protection for appropriate voltage ratings, voltage drop and current ratings for your system. So we're not going to go through all of those here. It's that same process of conferring with AS3008. One thing to point out is that there is no, so whilst I'll just make some notes here. Whilst AS3008 is a design selection, a cable selection standard for AC, alternating current cables, there is no Australian standard for DC. The direction from the Chief Health Officer is to use AS3008. So, some guidances around that. In terms of sizing cables, like there's sort of just a recommended process to go with, which is firstly work out the normal expected max current on the cable, and then go times 1.2. So it just gives us a safety margin of 20%. So whatever you're expecting, if it's 20 amps, you're expecting to be the maximum normal current on that cable for any cable. This is just like a cable sizing recommendation and overcurrent protection, cable protection sizing recommendation. Yeah, give yourself 20% safety margin. So yeah, if it was 20 amps, you'd jump up to 24 amps, and then that is your minimum. So greater than that, what's the greater than? That's our hungry crocodile. Goes that way. No, it doesn't go that way. It goes that way. Greater than that is your overcurrent protection rating. And then another 10% safety margin. So now you go your protection rating times 1.1. Greater than that. It's disappeared. How disappointing. Times 1.1, then you have your, of course, cable current carrying capacity. So that's just a rule of thumb, work out how much current you normally expect, give yourself 20% margin, size your protection rating, give yourself another 10% margin, and size your cable. You'll notice in AS3000 it references the non-conventional time current curve characteristic of fuses, and that they typically carry 10% more than their nominal rating. So that's where that whole 10% margin comes from. So basically we just want to go through and list off, what's the voltage and current rating of each of our isolators and protection, and what size cables are we going to use to achieve the current carrying capacity requirement and the voltage drop. So just a list of those. What do I want to do there? Any questions on that? Once you submit it, if you miss anything, I'll just make a note on it and send it back to you anyway. I'd say probably for many of us, a lot of the cable sizing, especially for the AC cables and the smaller DC cables like the solar, and that's probably pretty straightforward. It's probably more so like the battery cabling and that you'll have to refer to AS3008 just to double check current carrying capacity and that sort of thing.
You want to show us? You want us to show the word for like all of them?
No, not necessary. If it looks sus, that's when I'll ask the question and go, can you show me the formula? So up to you how you like to work it.
And for the battery cable, we'll use single core, AS3008.
Yeah, yep. So multi-stranded, so it's the same sort of stuff really as the PV1F as the solar cabling, just multi-stranded, flexible. Mostly because, again, it has mechanical stresses on it at some point where it runs out of the cable up the wall, out of the battery cabinet up the wall and all that sort of thing. When you have a look in these batteries as well, in the operation manual, it gives you a bit of a picture, I'm sure, somewhere in there. They do have a fuse, a switch fuse. That's like the cable entry just through some cable glands into the enclosure. Fan in the back. They've got a switch fuse unit in the side. And they show the terminations and stuff. Just like that. So there's one cable already runs into the cells internally, already terminated onto the fuse, and then I'm not sure whether they actually come with this cable. The outgoing cable that you can see coiled up on top in that other picture there. Just sort of coiled on top. I've installed a very similar one, BMZ, that had pretty much the identical setup. I think they may have come with some pre-made cables. So essentially what we'd be doing here, if they come with pre-made cables, great. If not, we'd just be running cables in, but then paralleling those cables that come out of there onto another isolator, switch fuse unit, multi-case circuit breaker, whatever, before connecting it to the inverter. So they'll have their own individual ones, but then you'll have one main for the whole battery bank, which is both batteries parallel together. Which is already there. It's that one that's part of the battery itself. Yeah, we'll just have one more that's rated for the two of them. So, you know, based on really the inverter's going to be the limiting factor in terms of current in and out of the batteries, because they can receive the 90 amps that we calculated. We'll program our inverter down to 90 amps for that. But then as far as discharge current goes, our multi-mode inverter's we base it on the continuous rating of 5 kilowatts. Remember we saw on the batteries, they can do up to 7 kilowatts each, so you could theoretically pull 14 kilowatts out of them, but the inverter's only going to do 5 kilowatts continuous, even though it can...
Rate your protection with.
Yeah.
I have oversized myself in protection.
Yep. So yeah. That's the plan there.
We want your protection to protect the inverter, then, to have something less than whatever the inverter can handle, max discharge.
I think the inverter may have internal fuse protection for itself.
Should.
It's more so just the cabling.
So you protect the cable.
This is now section 3 or stage 3 of the assessment. Document the design, so it's mostly documentation from here on in, including, you know, how the system works, operational documentation, and design like drawings, your schematics, block diagrams. So firstly, here again, this is quite likely to be a copy and paste exercise. The hazards and the risk control measures. It's just basically meant to mimic as if you've been to site now and you're making any adjustments as necessary. That's that one. Required installation equipment. So now that we know the number of products, the make and the model, you can just go through and fill that out from what we've already selected so far. So there's electrical schematic is to go in here. You can either insert it as a drawing or upload it as a separate document. You could do it by hand if you want, take a photo of it, upload it like that. If you upload it as a separate document, just make a note in here to say that you have. And there are examples, again, if you reflect to AT6, because you've got the exact same questions in there, it gives you references to the textbook where there's examples of what a schematic is expected to look like. I don't remember where it is right now. But it may, oh yeah, there's one on page 162 in the GCS textbook, first edition. But it may or may not reflect exactly the configuration you're doing. Like that one in there on page 162 looks more so to me like configuration 4. Both inverters are parallel connected in the switchboard. And then there's what looks like a manual changeover switch incorporated for the specified loads. So it's kind of like a hybrid between configuration 3 and configuration 4. But it gives you all the symbols, what they should look like and stuff like that, and layout. Just got to make sure you get the AC connection side of things to reflect yours, which you can get some assistance from these other diagrams that are not strictly schematics, but show you all the connections for each configuration from page 185 on, and configuration 5 is on page 187. So it shows you all the AC connections, what connects to what, to make sure we get that right. An equipment location diagram for question 3CII. There's an example of one on page 161. It's just like a bird's eye view or a plan view looking down at the building and the layout of things. Which again can be uploaded as a separate file if you prefer to do it that way rather than inserting it into this box. Just make a note of it though in this answer box that you have uploaded it separately. Because you can upload multiple files to the one location on Connect for your assessment. The next question is around the signage that you need. So specify the minimum signage requirements for the system below, your labelling. Remember, some are battery technology specific. So many of them will be the same as AT6, but some will be different because in AT6 you use lead acid. So you'll have some variations to the battery labelling. Just take note of those references again mentioned in this question at AT6 because you can look it up in the standards and it'll give you the specific different types that you need, the different battery technologies. But all your PV labelling will be the same.
Where was that labelling here?
In the standards.
Yep.
So AS 5033 for your PV labelling. And in AT6 at this exact same question, there's the actual references, like the appendix reference in the standard. And same with AS 5139, there's a reference to the section where you get all your labelling lists from. And it's slightly different because, like, for example, with your lead acid batteries, you'll have your, like, toxic fume, acid style labelling, which you don't have for lithium. Question 3D then is just this. As it says below, compile the documentation which would be used in the system owner's manual. So just bear in mind that this is to go to the owner to explain to them what they've got. So it's because sometimes people glaze over that statement and just sort of write it as if they're just writing it to me kind of thing. But what we want, and it doesn't have to be huge and long, succinct is good, but just addressing key points that the customer would want to know. Specify the system operating parameters. So describe for them, these few points below, how the system programming should respond to different circumstances. For example, grid blackout or not enough PV energy due to poor sunlight, client interaction with the system, what's required of them. So like in a blackout, you'll get those basic questions like, oh, do I have to go and switch anything on or off or whatever? But again, like we touched on earlier, your SP Pro, this electronic converter here is going to have the internal relay switch does that function. So it's something like 30 microseconds. As soon as it detects the grid outage, it'll switch the loads over to the battery. So it's as good as a UPS. So nothing required for the customer to do. Best thing for them to do is just familiarise themselves with the LED panel on the front of the inverter and the details that are on there. Things like earth fault alarms, of course, we actually address that later. But any alarms, they can obviously, the easiest thing is to tell them to call the installer. If there's not enough PV energy on a day where it's rainy, cloudy, what's going to happen? Okay, you're going to draw from the grid. You're going to use a bit more grid energy that day than you would otherwise. And what can we do? There's minimal interaction required from them. This is a good time to recommend to your client a preventative maintenance regime, maybe 12 monthly or something like that, where you come out and check up on it. Give them an idea of the expected life of all the key components. A lot of people just go conservative and go with the warranty periods, that's fine. And how to determine when components are at end of life. I always say that's, again, really best done through a preventative maintenance program where you can actually test it and find out how it's going and pick up things that are about to fail that way. So it's just a summary for your client about those different things. Then we want to document the system cost and performance at 3E here. So determine the total cost. There is a price list in the resource book in Connect. So that resource book that we referred to earlier, Do I have it open? Maybe not. Go back to it. So under the product data resources, this resource book here, there's a bunch of excerpts from the supply partners price list from page 28 on. So you should be able to find all of the major components in here, like the inverters and the panels and stuff like that, and price them up. You don't need to break your back on this. Like in terms of electrical and racking, it's fine if you want to do just a balance of system cost, you know, so that's it for the electrical, that's it for the racking, and just do it as major items to price it up. Don't forget, as it says there, remembering to allow for GST. So for you guys, if you're not familiar with pricing the systems, GST goes on first. So whatever, once you've added up all the costs of everything, you'll notice in the price list it's all X GST, and then you whack on, you know, your labour or whatever profit, and then your GST on top of that, 10%, and then STCs come off after that. So I don't know if you're familiar with calculating STCs. So you can go, just Google STC calculator. I always like to use the government one, doesn't matter, there's a bunch of different ones out there, but typically it's the first one that comes up, the REC registry, small generation unit STC calculator. And you just follow the prompts, just fill in the details there about, you know, what type of system is it, it's solar, what date are you expecting to do it. Doesn't really matter within the calendar year, it's only every 1st of January that it drops down, makes a difference. The rated power output, that's in DC. So if we were going to have a 6.6 kilowatt system, then you would do 6.6 there. What period you're going to calculate the STCs, typically we're going the maximum period. I don't know why anybody would use anything different. Maybe if it's a temporary system or something. Put in the postcode, I think 4800 is a Cairns postcode. Tick the box, whatever that means. Calculate. So 82 STCs. You can always look up like the current STC price. Basically, you could work on about $37 or $38 is pretty common at the moment. There's different websites that you can look at STC pricing and see what's happening with it. That's, yeah, most companies just give a point of sale discount in exchange for the STCs, and then they do the paperwork to submit the STCs. So that just helps with the pricing. Get your total price, add the GST, take off a point of sale discount for the STCs. That's that bit.
Power output, both of them, so like 10 kilowatt and 5 kilowatt, 5 kilowatt?
This is just your solar panels.
Okay.
Yeah, so if it was,
Go with that.
yeah, your 295 watters by however many, we did 25, didn't we? 295s.
Do you want us to go into further detail here about, or just a couple paragraphs about a breakdown and then what we've got as STC value and then just
Look, you could keep it as simple as just a total system price if you want. It doesn't have to go into great detail, but otherwise just those major components, the inverters, the panels, the battery, racking and electrical, and labour, you know, get a total price, add GST, take off that STC value. So yeah, we had 25 295 watt panels, which is 7375 watts, yeah. So that would actually be on that STC calculator I just did before, instead of 6.6 you'd be doing 7.375. Whatever that comes up at. The next step here, this is one that gets a lot of people hung up. Cost per system lifetime kilowatt hours. Okay, what is system lifetime kilowatt hours? How many kilowatt hours for the lifetime of the system it's going to produce? This is best worked out on the number of kilowatt hours the load's going to use. So we size the PV array to be able to not only provide the loads but also overcome the losses in the system. But that's just transmission losses. Like, it's not really meaningful to the customer for us to price it on their transmission losses, you know. Like, as customers, they only get charged for what comes after the meter, not for what it costs to get it from the coal-fired generator through all those lines to their house, you know what I mean? So what did we design the system for? Daytime of 13 kilowatt hours, peak for 9 kilowatt hours. So essentially 27. Is that right? 22 kilowatt hours of load usage is what we designed the system for. Per day, 365 days per year, times whatever number of years you're sort of offering this system to the customer for. Some people go super conservative and go 5 years, sort of like minimum warranty periods. So that's like 40,150 kilowatt hours. So the way to get the cost per system lifetime kilowatt hours is you work out whatever the system cost was. Let's say, I don't know, for example, 50 grand. Cost per system lifetime kilowatt hours. So yeah, 5 years isn't very much. So you want to divide your cost of the system by the kilowatt hours it's going to produce. So this example, 50,000 divided by 4150 would be $1.24 per kilowatt hour. A lot of people do that the wrong way around, and they do kilowatt hours per cost, so they do 40,150 kilowatt hours divided by the 50 grand, or something like that. But we're trying to work out for what the customers outlaid. If they outlaid 50 grand, and they're going to get 40,150 kilowatt hours out of it, what's the how much do they pay per kilowatt hour? Does that make sense? So they pay. It is, that's right. And that's why it's an interesting exercise. You wouldn't use it as a sales tool by any means. But for us to reflect on here, it's like, compared to grid costs, it's expensive. But I mean, I've just pot shotted 50 grand. It might be a bit expensive. Plus, 5 years is a short period, you know. You might, yeah. It just depends on how risk averse you are as a supplier. You could build in some warranty extensions and stuff like that. Because, I mean, most of your warranties, your Fronius is 5+5, so there's 10 years there. Your Selectronic, as long as you connect it to the internet, it's 10 years. Your battery's 10 years. So you could easily make it 10 years. You know, it'll start to look a lot better if we made that 10 years and made this 80,300. And they'll halve that, you know. 0.6, it's already looking a lot better, isn't it? Then here, what we're going to do is actually work out, so that's their per kilowatt hour cost because of what you charge them for the system. But now down here, what we're going to do is compare what they were paying for grid electricity beforehand, and now with the savings we've implemented, how much it's costing them per year. So from our initial, when we first came to the customer and they gave us their load detail, for the summer usage, that's what we're filling out in this first table, see how it says determine the yearly cost of electricity prior to enacting any changes. So I've got one I filled out previously, I'm sure. So their usage was 36 kilowatt hours per day for summer, and it was 30 for the rest of the year. Their rates, remember, it was just tariff 11, which we filled out earlier as that whole 0.278278 value. $10.018 per day. So we're just working out literally what their average billing cost was for their electricity. We'll just go easy and call it 90 days for summer, 76 the rest of the year. Supply charge was 97. Oops. Not kilowatt hours per day. So basically, their original cost before we came along and did anything was $3,500 odd bucks a year. Then it asks us in the next table to compare if all they did was the energy efficiency and load shifting stuff that we recommended, which was what altered their overall usage down to the 27 kilowatt hours per day. And obviously that would have still been on the tariff 11 rate. No. Yes, sorry, that was before changing the tariff. So then we see that, yeah, okay, saved them just under $500 a year by implementing those measures. And then finally we bring in the whole strategy where now we've got the system included and the tariff 12A. So there's now zero usage during the peak period on average, what we've designed the system for. during the day and night usage, there's only the night time left, which was 5 kilowatt hours. So it's the same for the rest of the year, we assume, if they're going to use the system the same way, just 5 kilowatt hours at night time. When they change the tariff 12A, their costs will be different. Some day and night usage. With regards to the solar feed-in credit, it's going to be, fairly incidental. But again, just working on averages like the rest of it, we can calculate what it would be on average because we upscaled our system. Remember, the minimum we required was, how many panels was that? 6.2 kilowatts or something, wasn't it? 21 modules, and we bumped it up to 25. So basically the difference is those 4 modules. So we just need to calculate 4 modules at 295 watts at the efficiency that we used built into the peak sun hours, that there, 4.298. That allows for our average peak sun hours and the efficiency of the PV array. So that number there we're going to use to work out the extra 4 panels we added on to make it a 25 panel system. How much excess PV energy is that going to produce on average, and that will be our feed-in tariff. So 4 by 295. 5,062 watt hours. 5 kilowatt hours. So that's going to be our solar feed in. So we're looking at a cost of $572 a year, down from $3,500, so saving about $3,000 a year. And we want to further show that in this next question here with 3EIII saying, based on the savings made by implementing the full strategy, estimate the system cost and calculate the simple payback period for the system. In other words, how much the client has saved on their energy usage as opposed to their original expense, then divided into their financial outlay for the power system. So annual electricity cost saving is just what their original amount was, $3,500 odd, minus the new cost, 500 and something. $29.90. Divide the customer's cost of the system by this saving. This gives a simple payback period. We call it simple because it doesn't really allow for a couple of other things like the cash rate, CPI'd, being corrected year on year for inflation. Any interest that would have been charged or earned, for example, on that cash. The other thing too, which to be honest is a bit of an oversight on the whole design, is just degradation. So, for however many years we're offering this to the customer and showing these sorts of numbers on their savings and their benefits and that sort of thing, we should also build in the degradation. For example, on the solar panels, they've got typically a performance warranty that ends up at around about 80% or so after 25 years. And the simple way to do that is that we just build it in at the beginning, actually allow for that 20% loss, just add extra 20% on. Things like that can be considered. We just keep it relatively simple in this assessment. Any questions on that so far? We came up with those numbers. All good. From here, it's just tying up some loose ends, following elements that go into an owner's system manual. We just want to extract and summarize the key information. For example, key battery system information, manufacturer being Sun and Shine, capacity like the 8.5 kilowatt hours total, and I think it was 6.8 kilowatt hours nominal. off the data sheet. Maximum charge and discharge, we've seen these values. Chemical type, you'll find that in the operation manual. So not just lithium, but the specific chemical type. In the operation manual, you'll find that it's actually in that technical key variables here on page 33. And you'll see it's lithium ion NMC, so nickel manganese cobalt oxide, which you see referred to in the textbook when they're talking about the lithium battery technologies. And in one of the videos in the PowerPoint as well, they talk about the different types and what's being used by different companies. Simple stuff like response to earth fault alarm, it can be as simple as telling the customer to just contact the installer as a first port of call. Some people will choose to tell them to shut it down first. Shutdown procedure, what we really want to stick with is just the same concept as with solar. And it's about load shedding. Just for example, if you were shutting down a big site, like a big commercial site with multiple buildings, you're not just going to walk up to the main switch for the whole site and flick that off. Typically you're going to load shed with different buildings along the way, subboards, distribution boards, that sort of thing. And so it's the same concept even on a smaller scale. We load shed, take the AC loads off first, and then work your way backwards to the DC. So the DC, direct current, being a constant current, is a lot harder to break an arc than it is with AC. So it makes sense to break the AC arcs first, to get rid of the load first. Your startup procedure's just the opposite. And then 3F part 4, we have maintenance procedures, activities and frequency. And that there, again, there'll be a reference, I think, in 86 to this question, which shows you both in AS 5033, I think it's Appendix C, talks about it, maintenance, and for some reason I want to say Appendix H something in AS 5139 is about maintenance for the battery system. So that's where we build out just maintenance timetable for the customer to be kept with their power system manual. And finally, warranty information of key components just off the manufacturer's website. And that's it.